All right, this is AP Calculus. We're doing the final review packet starting on Unit 11 and going back through Unit 7. That's all the free response questions. All right, for number 1, we have these two functions. All right, I see what's going on, and we need to find the area of the region R. So this is going to be top minus bottom, but the problem with this is that we don't know this intersection. That intersection doesn't look like it's exactly 1, so I'm going to have to graph that. So if I come over here to my calculator, I'm going to enter these functions. I'm going to do the e to the x first. So e to the power of negative x squared. And then this next function is going to be 1 minus cosine of x. I did hit cosine, I thought cosine of x. Good. And it looks like our window should be at about 1.5. You can see over here that's our maximum. So if I come to window, my x-min, I guess 0, right? 0, enter, and I'll go 1.5, enter, zoom, 0. That will graph. It looks pretty good. To find the intersection, we're going to go to second and then trace to do the calculation. And we want to do the intersect, so I'll hit 5. And just enter, enter, enter. And I get 0.942 if I'm rounding to 3 decimal places. So I'll have to say I should go back to my pencil. 0.942 is this spot right here. Cool. Now we have our bounds for our integral. And again, your general formula, your speed sheet definition here is just going to be the integral of your bounds of top minus the bottom. And our top here is that e to the negative x squared. So our integral is going to be the integral between 0 and that 0.942. And the top is going to be e to the negative x squared. And then I'm going to subtract the bottom function, which is, okay, so be careful, because all of this is one function, we need to make sure that we put parentheses around it so that when we do a subtraction of the parentheses, it will distribute the parentheses correctly. So I'll say, in parentheses now, 1 minus cosine of x. All right, and all that thing, to be formal about this, this should have a dx on it, and I'm noticing that I'm not really going to have enough room for my parentheses, so if I move this over a little bit, put parentheses around this, dx, and we're ready to solve. This will be approximated by the calculator, so we'll come over here a second and quit. And math 9 to do an integral between 0 and go up here, 0.942, and then this is going to be bars right, enter 1, minus bars right, enter 2, with respect to x, enter. And we get 0.591 if we round it. So I'll say this is going to be 0.591. Cool. And I'll box it. I tried to make a box, whatever. Excellent. Part B. I'll zoom back out here. Find the volume of the solid generated when the region R is revolved around the x-axis. So the first thing that pops out to me is this word revolve. Revolve means that I'm going to be using a pi because I'm going to have a circle, and circles have pi in them. And I always forget my pi. So first thing, I'm going to do pi, and I'm going to go ahead and give the speed sheet definition here. The general idea here for any solids of revolution, you're going to do pi times outer minus whatever you're revolving around, squared minus inner minus whatever you're revolving around quantity squared. All right, so for us, we're going to have pi, the integral, and I think the bounds are still going to be the same. Nothing's changed there. 0 to 0.942. And then we're going to do outer. So where's outer? We're rotating around the x-axis. So if it's the x-axis, that means that I'm going to have this line right here, and I'm going to be rotating around that line. So my outer function is really this curve, and my inner function is this curve. So this is going to be my first, this is going to be my second. All right. So coming down here, it's in the same order that I had it before. I can zoom in even farther to get my handwriting really nice when I zoom back out. E to the negative x squared. And what am I rotating around? I'm rotating around the x-axis, so I could say minus 0, but that's kind of silly. So I'm just going to say that function, quantity squared minus my inner function, so I'll put parentheses, 1 minus cosine of x, quantity squared. And that whole thing needs to be with a dx, so I do need to grab everything, move it over a little bit, so I have some parentheses here. The whole thing dx. And let's do that on the calculator. So I'm going to come over here and do another, I'm going to do my pi first, so second pi. And then I'm going to do math 9, same bounds, 0.942. Vars right, enter 1. Okay, square that. And then I'm going to subtract vars right, enter 2 squared. And all that's going to be with respect to x. 1.747 if I'm rounding. So this is equal to 1.747. And we will box that. That is our final answer. Didn't hold it for the square, but that's okay. Moving on. The region R is the base of a solid. All right, cross sections. What are we going to do? Each cross section is perpendicular to the x-axis. Okay, so that's kind of our first key thing. What does this mean? Perpendicular to the x-axis. Well, x-axis is running this way, so perpendicular will be running up and down. So every time that I'm taking a slice, I'm doing a slice, 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 slice. That's the direction, as opposed to this way, right? And the shape is going to be a square, and then we're going to find the volume. Okay, so if I'm trying to annotate this thing in terms of the 3D drawing, and I know my artistic skills are not the best, I'm just going to choose like a random slice. So if I have this line right here, and I'm going to pop that out into the third dimension, so I'm going to go out this way and say that is my square. And I need to ask myself, well, first of all, what is this length? This length is going to be the top minus the bottom. This is always going to be our e to the negative x squared minus 1 minus cosine of x. And that's this length. And because this length and this length are the same, this length will also be e to the negative x squared times 1 minus cosine of x. So I know the area of that square, and I can go ahead and do that down here. I always just like rederiving where the area comes from. The general speed sheet definition for this one is going to be the integral of your top minus the bottom quantity squared is the general idea. So for us, it's going to be the same bounds, 0 to 0.942 of our top, which is e to the negative x squared. And I don't know why I'm zoomed so far out because my squares are not looking very nice. I'm going to go ahead and redo that. E to the negative x squared. And then subtract. And then I do need parentheses again. Be careful. I have the 1 minus cosine of x. That thing is in parentheses, all right? And then I want to do that whole thing quantity squared. So I'm going to put square brackets here. That whole thing quantity squared and dx to make it formal. Excellent. So if you're thinking about what is what for area, just remember that all of this is your area, and then the d of x is the thickness, right? How thick is each of those slices? And eventually that thickness basically goes to 0. But let's go ahead and actually do this in the calculator. So we're going to do another math 9, 0 to 0.942. And it's going to be, okay, I want parentheses now because remember, I have to have this set of parentheses that'll end and then square it. So I'm redoing this parentheses right now. So parentheses, and then vars right, enter 1, minus vars right, enter 2, end parentheses, and square all of that with respect to x, enter. There it is, 0.461. So let's say this is going to be, whoa, 0.461 and box it. For number 2, we do not have a calculator, so that's why I've turned it off. And we are trying to find the area. So I'm noticing that we have two different functions. We have a square root of x, and we have the linear function x over 2. Linear because this is an x to the power of 1. And linear means that it's going to be that straight line, and the square root is going to have that curvy function. So I know that this top function is going to be, I can zoom in here to label it a little bit neater. This is going to be the square root of x, and the bottom function is going to be x over 2. So whenever we have a function on the top and the bottom, it's always going to be, and we're trying to find the area of it, our speechy definition is always going to tell us we're going to take the integral between whatever the bounds are of our top minus the bottom. In our case, that is going to be the integral of the top, which is the curvy function, the square root of x, and the bottom is going to be x over 2, and that whole quantity is going to be multiplied by dx. But what are the bounds? So the bounds are going to be the x coordinates. So I have the x coordinate from 0 all the way to 4. So if I come back down here, I can zoom in and say that this is between 0 and 4. All right, so I noticed that when I take the integral here, I have to do it by hand, right? Because it's without a calculator, and there's no house. So some people think, oh, I might need to use tax person, but notice that the power up here, there isn't a power, so it's a power of 1. There is no, this is not a part of the house. You have two individual houses, I suppose. You have like this powerhouse here, but both of them are going to have an inner that is x, and therefore the inner is 1. You don't really have to worry about tax person in this case. So I'm going to go ahead and rewrite this without the radical symbol, and that'll help us a little bit. So this is going to be equal to the integral between 0 and 4 of x to the power of 1/2 minus, and I think another easier way to think about this is, no, I was going to say 1/2 of x, but I think it's going to be the same thing as just x over 2. I don't think that makes it any easier. That function dx. Okay, well, we're ready to do the antiderivative. We don't need to pay tax person, so this is going to be, it was x to the 1/2. 1/2 is going to be, we're going to add 1 to it, so we're going to get 3/2. And then we need to divide by 3/2. And dividing by 3/2 is the same thing as multiplying by 2/3. And then we're going to subtract. This is going to go x to the power of 2. It goes up a power, right? The old power was 1, and now it's going to go up to the power of 2. And then I divide down by 2. But remember that we already have a 2 down here, so if I divide by 2 again, I can really, here, I'll just say 2 times 2. There's 2 of those 2's in the denominator. And I'm done taking the antiderivative, so I'm going to not have a plus c. I'm going to have an evaluation bar between our bounds from 0 to 4. All right, so we're ready to plug in now. And I think I have enough room if I just finish it up over here. So let's plug in 4 first. So I'm going to have 2/3 and then plugging in 4. So 4 to the power of 3/2 minus, and then I'm going to plug in 4 again. So 4 quantity squared. Oop, I can write a little bit neater. 4 quantity squared all over, and then that denominator simplifies to 4. All right, so that's the first half, right? That's what happens when we plug in 4. And then we needed to subtract what happens when you plug in 0. And notice that when you plug in 0 to each of these x's, I'm going to have a 0 to the power of some number, which is still 0, times a number, which is still 0. Everything here is 0, everything here is 0. So I'll show my work by just saying 0 minus 0. You don't have to worry about the second half of that. It's all 0. All right, so I just need to simplify the first half of that. What is that going to look like? I think the hardest thing to deal with here is this 4 to the power of 3/2. And the way that I'm going to do this is I'm going to rewrite that as 4 to the power of 1/2 to the power of 3. And again, I'm really just multiplying powers. 1/2 times 3 is the same thing as 3/2. But the reason I've written it like this is because we can now say that this is going to be the square root of 4 to the power of 3, which is equal to 2 to the power of 3, which is equal to 8. All right, so I know that's going to be 8, and then I still need to multiply that 8 by 2 and then divide by 3. So I'm going to have 16/3 here. 16, oh, I don't want to go back to blue, actually. come back here and say, in blue, that's going to be 16/3 minus, and I'm going to have this fraction. So this is going to be 16/4, and 16/4 is just 4. So I can say that this is minus 4. And I need like fractions in order to get this simplified. So I'm going to now change this to 16/3 minus. I'm going to multiply the top and bottom of this fraction here by 3/3, and that's going to turn into 12/3. Minus 12/3. 16 minus 12 is 4. And it looks like 4/3 is our final answer. So I'm going to go ahead and box that. Again, not quite the rectangle I was looking for, but we did get our answer. Yeah, let's move on to part B. All right, so saying that region R, okay, that's the area, is the base of a solid. Okay, so we're going to have some sort of cross-section. And indeed, yeah, we have cross-sections. That just means we're having like squares or something, or semicircles. Okay, perpendicular to the x-axis. So that means in terms of our problem, the x-axis is running like this. Perpendicular to that is running up and down. So every single slice of this function is going to be running this way as opposed to going this way, right? And then the key point here is they're going to be squares, and we're just trying to find the volume. So the square volume has a speed sheet definition that you should know. Whenever you have a square cross-section, it's always going to be the integral of the top minus the bottom, and that quantity squared. And it's still the same top minus bottom, so I can basically rewrite that old formula. Same bounds and everything, right? 0 to 4. Top was the square root of x, and the bottom was x over 2 quantity squared dx. And it doesn't say write but do not evaluate. It actually wants to find the volume, right? We're finding the entire number. All right, so again, it's kind of a pain with no calculator, but it's a good way to test this. So the test our problem solving, our mathematics here. So the problem here is you can't do anti-powerhouse because we have this pesky power of 2 that's in the way. So in order to get rid of that, I'm going to have to actually multiply it all the way out. And I know that some people like the shortcut, but I think I'm going to do it the other way as well, and I'll tell you why the shortcut kicks in. So first of all, I'm going to rewrite this as the integral between 0 and 4 of x to the power of 1/2 minus x over 2 quantity squared dx. Again, I basically just change it to the power of 1/2 to make it easier for us. And I need to find what that expands to. So, and I'm going to do a separate problem. I'll do like a different color maybe. And I'm going to say, okay, what is x to the power of 1/2 minus x over 2 quantity squared? I want to find a better way to rewrite that. And the way that the long way of doing it is to do the following. I'll do a little arrow here, is to make a square. If I hold this, it should turn into a square. Hooray! I want a straight line right there, and a straight line right here. And I'm going to put that as the side. So I have x to the power of 1/2 and x over 2, x to the power of 1/2, x over 2. And I have to be careful here. I do have a minus x over 2, right? So don't forget that there should be a minus sign in front of the x over 2. And I'm just going to multiply those together. Again, what I essentially have here is this side times this side, or again, these are going to be multiplied together. And when you multiply and you have the same base, it's still going to have the same base x, and then you're going to add these powers. A half plus a half is 1, so this is x to the power of 1. And then be careful here. So now we have these two being multiplied together to get this cell, and I have x to the power of 1/2 and x to the power of 1. I'm going to add those two together to get 1.5, or 3/2, and this is going to be x to the power of 3/2 over 2, and that is a negative, so don't forget that too. And then you should have the same thing again. So I have a negative x to the power of 3/2 over 2. And then finally, I have a negative times a negative, so I do have a positive down here. And x times x is x squared. The denominator is going to be 2 times 2, which is going to be 4. All right, so I have all my pieces, and I can add them all up now. When I add up the area, that's going to be equal to, I have an x to the power of 1, which is just x. I have 2 of these, so I have minus 2 of these copies of, and I'll put parentheses here, x to the power of 3 halves over 2. And then finally plus my x squared over 4. I've just rewritten all of the area. This is all of the area inside of the square. And I can simplify just a little bit because I do have a 2 and a 2 that can cancel out, right? So I can say, yes, those do cross cancel. And this is really equal to x minus x to the 3 halves plus x squared over 4. And that's really the term that I want to integrate. And I'm sure at this point you're like, wait, that was a lot of work. Isn't there a faster way? And yes, there is. And the way that I've always done this in class is to say you're going to square the first, double the product, and square the last. And that will always jump right here. That is a faster way if you can memorize that. And if you can't memorize it, you can go through the entire long way and it will still work. Again, AP Calculus is time, so you kind of do want to know the faster way. So let me write out the faster way just in case you want to see that. The rules again, and this is whenever you have a square. I didn't have the highlighter tool on, but whenever I have a square, you're always going to do the following 3 things. You're going to square the first, you are going to double the product, and then finally square the last. And this is where I'm getting to explain why that trick works. So notice that when you square the first, that came from the first term times the first term, which is the first term squared, which in this case was x to the power of 1. Why do we say double the product? Well, the product of these 2 terms is really these 2 terms right here, yeah? And that gave you this spot right here. And there were 2 of them, which means that we were doubling that product. So these 2 came from doubling the product, and then finally squaring the last again. Negative x over 2 did give you the x squared over 4. So shortcut, long way. Anyway, let's go ahead and fill this thing into our integral and actually do some more math. So over here, I can now rewrite this integral. This is going to be the integral from 0 to 4 of all of that thing that was x minus x power of 3 halves, and then plus, I'm just trying to remember, x squared over 4, right? I think so. And to be formal about it, this is a free response question. I'll write the dx here. And again, should you be worried about tax person? Always. But in this case, you don't have to worry about it because all of the houses are kind of small. That's a small house, small house, small house. You can kind of ignore them. And I really should have the parentheses right there, huh? Just take the antiderivative of each piece individually, and we get, so this is going to be x to the power of, it's going to go up to the power of 2, and then I'm going to divide down by 2, minus, okay, this is going to be x to the power of, it goes up a power from 3 halves to 5 halves, and then divide by 5 halves, and I should really move you over a little bit. That's going to be 2/5. And then finally, I'm going to add, this is going to be x to the power of 3, and then I'm going to divide down by that 3, so I have divide by 3 times 4. Okay, and that's going to be evaluation bar between 0 and 4. I think I'll have enough room down here at the bottom. Oh yeah, I got plenty of room. Wow, there's a ton of white space down here. That's what happens when you zoom in so far, right? Okay, so plug in 4 first. So that's going to give us the quantity of 4 squared over 2 minus 2 times, here we go again, plug in 4 to the power of 5 halves, which will be a little bit tricky, but we can do that. And then finally plus, and then I'm going to have 4, the quantity of 4 cubed all over 12. And maybe, I'm feeling that there's actually an easier way to do that. I'm going to leave it as 3 times 4, and you'll see why in a sec. That was the first half, so I should put that in parentheses. And then I'm going to subtract the second half, right? What happens when you plug in 0? When you plug in 0, all 3 of those terms go to 0. That goes to 0. All of these go to 0. So I'm going to show my work by going like 0 minus 0 plus 0. You don't have to do that on the AP test. I'm doing it for my answer key so that everyone can see that I didn't forget to plug in 0. A really common thing is when we have some sort of exponential functions, which we don't have in this problem. But if you did, you always have to remember to plug in that 0 because you will get a number out. All right, so jumping into the gritty math here. So I have 4 squared, which is 16. 16 over 2 is 8 for our first term. The second term is going to take a little bit more work. So again, I'm going to go do a side problem. How do I do 4 to the power of 5 halves? I can do like a little wavy line to say I'm working on a new problem. So the way that I think about this one is it's going to be 4 to the 1/2 to the power of 5, which means this is really going to be the square root of 4, and then that quantity to the power of 5. Square root of 4 is 2, so this is 2 to the power of 5, and 2 to the power of 5, I think it's 32, but I always have to double check those. I'm frequently wrong. That means I have 5 2's. 1, 2, 3, 4, 5. 2 and 2 is 4, 2 and 2 is 4, 4 and 4 is 16, 16 and 2 is 32. Okay, I got it right. So that means I'm going to come back over here and say that's 32. But remember, that was just, 32 is just this term. It does not account for the 2 and the 5. So I'm going to go ahead and rewrite that as, oh, I do want to go back to blue here. So I'm going to say minus, I have that 2/5 times 32. Maybe I can just extend that bar over, sure. And then plus, okay, so this is the trick that I was thinking of. I'm seeing that we have a 4 to the power of 3 and this 4 to the power of 1, and I can just subtract the powers, 3 minus this 1, to get 2. So I'm going to rewrite this as 4 to the power of 2 all over 3. And we're pretty close. I think I can just keep going down instead of moving to the right. We still have an 8 here. So 2 times 32 is going to be 64 over 5. Ooh, that's not a nice number. There's no divisibility there that makes it come out nice. I'm just going to leave that as 64 fifths. Kind of gross. And then finally plus 16 thirds, and those do not have like denominators. So we'll treat that as an 8 over 1. And what do we need to multiply everything by to get like denominators? Well, it looks like the 5 and 3 are going to make a 15. Oop, I guess I double tapped the screen. Didn't mean to do that. So essentially what I'm going to be multiplying, I'm going to be multiplying the 16 over 3 by 5. I'll do the 64 over 5 by 3 and 3. And then I'll have to do 15. Ooh, and I do want to write a little bit neater. 15 over 15, and then theoretically, man, my handwriting, theoretically I should now have like denominators, and I should put parentheses around that to keep it organized. All right, and once we do that, we get, I think I can just come down here, 15 times 8. So if you're ever struggling with your 2-digit multiplication, you can do it the long way, but the way that I do it in my head is I do this, 15, I should do this in black or something, let you know I'm working on a different problem. All the math tricks. 15 times 8. How do you think of that in your head, Mr. Sindel? Well, I think of this problem as 10 plus 5 times 8, and then I distribute the 8. So this is going to turn into 80 plus 40, and that's just 120. So this is going to be I do want to switch back to blue. 120 all over 15. Didn't I just say I wanted to turn it into blue and I didn't even follow my own advice? Come on, Mr. Sindel. 120 over 15 minus, all right, 64 times 3. And this one I'm kind of doing, there's not a trick that I'm thinking of. I have a 12, which means I have 2 here. Carry the 1. 3 times 6 is 18, and that 1 is carried, so it's going to be 192 over 15 plus 5 times 16. I am kind of using that same trick that I used over here in my head, so I'm seeing the 30, and that's going to be 80 over 15. And oh, this is pretty cool. So check this out. If I take the positives first, this term and this term, which are both positive, not the negative term, right? I have an 80 and 120, which makes it 200, and then I can easily subtract 192 from 200 to just get an 8. So this problem is going to be equal to, I'll show my work a little bit. That's going to be 200 over 15 minus 192 over 15, which is 8. over 15. 8 has multiples of 2 and 2 and 2. 15 is just 3 and 5. So I can't simplify this at all. And that's my final answer, 8/15. Let's go ahead and box. Whoa, I don't know what I'm hitting on my iPad. Capture a quick note. Well, that's cool, but I don't want to do that. Go away. Please. Okay, thank you. Excellent. All right. I know I'm taking way too long to go through these, but I like to be thorough where I can if I have time. Yay, okay, so this one we have to write, but we're not evaluating. I love the words do not evaluate. So we're having the word rotate. Every single time I see the word rotate or revolve, I always immediately write out a pi because I so often forget my pi. So we have a pi, and then we have this horizontal line y equals 2. So it's really important whenever you see this line y equals 2 to draw that. So up here, y equals 2 is going to be this line right here. Why is it important to draw that line? Because we want to know which curve, which function is farthest away, because that's one we want to do first. Notice that the outer, the farthest away, is now going to be the line. Normally, our first function has always been the square root of x, but now our first function is going to be the line because that is farthest away from our line that we just drew. So we'll do this one first, that's going to be our outer, and then our inner is going to be this curvy square root of x function. And then we just use our formula. So remind yourself what the formula is. The formula, and I do want to make my pi look a little bit nicer. The formula for revolution is going to be pi times the integral of outer squared minus inner squared. And for us, that's going to be pi times the integral between still 0 and 4. Those bounds will not change unless we somehow need to do a vertical line or something. Outer is going to be now that x over 2. Okay, so, and I should really fix this speed sheet definition because that's the basic one, but the non-basic one looks like this. It's going to be outer minus whatever line is, I'm just going to call it k, quantity squared, because I realize that we're rotating about a line, not just by the x-axis. And then subtract the inner minus k, quantity squared. So we have the outer, which is x over 2, and then we have to subtract whatever the number is. And in this case, our number is 2. So I'm going to come down here and say minus 2 quantity squared. And then the inner is going to be that square root of x function. Minus 2 again, that's our constant function, quantity squared. Now this whole thing needs to be multiplied by dx. So I'm going to put another set of parentheses. I'll do like a square bracket to differentiate between the round parentheses versus the line, the horizontal and vertical lines of the bracket, right? Makes it a little bit clearer. Dx. And that's it. That's all we needed to do. And we're on number 3, which is also no calculator. So, all right, just reading our problem. It's nice to know that it is a semicircle. Remember that the definition of a semicircle is exactly half of a circle. It doesn't mean some partial circle. And there are line segments. Okay. And okay, so this means that we have an accumulation integral. And one thing that we have to worry about is the fact that our accumulation integral starts at -3, which might cause issues. And indeed it does in part A. How many parts do we have again? We have 4, all the way through D. And I want to make one point that I don't know if I've ever made before, at least not in this year that I'm recording this. When I'm giving you a lot of room for part C, that usually means that it takes more work. And it is true for this class, but on the real AP test and the practice test that you'll be having at the end of this packet, there's going to be an equal amount of room for every problem, so it doesn't give it away with giving you extra space. So just as a heads up. So let's find g of 0. So notice that g is the function. It is this accumulation integral. Every single time you see an x, change it out for a 0. You see an x, change it out for a 0, right? So I'll say g of, I don't want to say g of x. I'll say g of 0 is equal to, and then I'm going to rewrite. I'm essentially just rewriting all of this, but in the place of that x, I'm going to swap it out for a 0. So I'm going to say between -3 and 0 of f of t dt. Okay, that is g of 0, but we need to find what that is. And luckily here, I thought I was going to have to switch these around. -3 and 0, that is in the correct order, right? You want to go from the left to the right, and -3 is before 0, so we're actually in good shape. If this was a +3, then we would have had to switch these two bounds around and then make it negative, but we don't have to do that in this case. Lucky us. All right, so we're just trying to find the area between -3 and 0 on our graph. So again, -3 and 0. I'm trying to find this area right here. And I'm going to make a straight line, or attempt a straight line right here. And how do I want to cut this up? I think I want to make a triangle right here. And I really want this to be nice. Oh, can I just grab this line and drag it down a little bit? Is it going to let me? There we go. I want it exactly right there. Okay, so that's how I'm going to divide up that area. And I see that there's a rectangle down here and a triangle up here. The rectangle is going to be 3 by 1, which has an area of 3. This is going to be a triangle that has the same dimensions. Remember, you're kind of pretending that there's a dashed line up here. And do I have the ability to make a dashed line? No, I don't. All right. So it's going to be exactly half of that previous rectangle. So this area is going to be 1.5. And if I add those together, I get 4.5. So come down here. That area is exactly 4.5. Excellent. Moving on to g prime of 0. Well, g prime of x we need to find first, and then once we know what the derivative of our accumulation integral is, we can plug in 0. So if I take the derivative of the left, that means I'm also doing the derivative of the right. So I have to take the derivative of this accumulation integral. The quickest way to explain this is to say you plug in the x. So I have f of every word that you see a t, change it out for an x. So it's f of x. And again, the integral symbol and the dt go away when you take the derivative of an integral. They kind of cancel each other out. And then the only thing that you have to worry about is to multiply by the derivative of the thing that you plugged in. So in this case, we need to multiply this thing by x prime, or 1, which is kind of insignificant because it doesn't matter. But what if this thing was an x squared? Then I would have to multiply by 2x, which would change the entire problem. Luckily, we got a nice, easy problem. So essentially, g prime of x is just f of x, which basically means the height, right? So if I look at this graph, it's now asking for height on this graph. And what are we after? We're after g prime of 0. So if I rewrite that, g prime of 0, I'm plugging in 0, so f of 0. This is, I'll write this down here, this is height. Height at x is equal to 0 on our function. So if I come over here to 0, you can clearly see that at 0 we have this height up here of 1. So I can come down here and say that is exactly equal to 1 in blue. Cool. On to part B. Find all values in between -5 and 4, which I think are the bounds of the graph, right? Yep, -5 and 4 are the bounds at which g, oh, not f, but g, attains a relative maximum. All right, so we need the definition of g relative maximum, not f relative maximum. So g relative maximum. Do you know your speed sheet definition for this one? Well, a g relative maximum is where g prime goes from a positive to a negative. And you'll notice that we have a g prime in our definition, so I do want to make this arrow look a little bit cleaner. Better. We need to find what g prime is, and hey, we did that back up here, right? We know that g prime is just f of x. So really, if I'm rewriting this, I'm really saying, where does f go from a positive to a negative? And now we have a graph of f up here. So f on a graph of f is height. So again, if I'm rewriting this yet a third time, this is going to be height. Make that h a little bit bigger. A height that goes from a positive to a negative. So doing our analysis up here, where do we have a height that goes from a positive or a negative to a positive, right? no, positive to a negative. I'm backwards. So notice that over here we have a negative height that goes to a positive height, and that is backwards, right? We want a positive height to a negative height. So this one is not what we're looking for. Over here, we do touch the x-axis, but we go from a positive height again back to a positive height where there was no sign change. And then finally, we do have one point down here where we have a positive height down here to a negative height, and that's the one that we're looking for. That's a relative maximum. And that happens at this x-coordinate 3. So your final answer will look like this. It'll say like relative max at the x-coordinate 3. And you do want to have the, I know we already wrote our reason essentially over here on the left, but I'm going to rewrite it again, make it easy for the AP grader, make it easy for Mr. Sindel to give you those points. You'll say, because, you'll say, not F, I want to say G prime, because G prime is the original definition. Always go to the original definition, because G prime went from a positive to a negative, and that is the definition that we're after. And moving on to part C. Find the absolute minimum. Okay, so this is a little bit different than the previous problem, because the previous problem was asking for relative minimum, and now we're after absolute minimum. Whenever you have absolute minimum, the only way to do that is with a table. And that's kind of annoying because I'm pretty sure, yeah, this is a no calculator question, so we have to do a table without a calculator. All right, so let's go ahead and set up our table. We have this horizontal line right here. We have our t values. All of our work is going to be shown there. And we'll say these are the x values. And again, we need to put in the start and end. So we need a -5, and we need a 4. And then we need all critical values. Really, we're after relative extremum. So I'm going to say that this middle section right here is devoted to relative extremum, just meaning a maximum or a minimum. And that means that we are going to exclude the critical value that is not a relative extremum. So just to remind you, again, the speechy definition of a relative extremum, I'll write it down here in a different color, let you know I'm doing something else. A relative extremum is where you have a, if we're talking about G, we're talking about a G prime sign change. And because G prime is the same thing as F, we're looking for an F sign change. And I've already made the analysis before, but F is height. So is there a height sign change? And if you come up here and look at the graph, there is not a sign change here, even though we do touch the x-axis. This is a critical value, but it's not a relative extremum. We only have two relative extremums. We have this minimum and this maximum. Those are our points that we want to include. So I'm going to include this point, -4 and 3 on our table. So come over here and in blue say -4 and 3 need to be on the table, but we don't need whatever that other one was, 1. Your table is still complete without it. Okay, we're going to be doing start plus change is equal to end. And do we have any initial value? Is there some start? No. Okay, so that means our start for all of these is going to be 0, which is pretty lovely. 0, 0, 0, 0. And I'm going to go ahead and eliminate one of these right now, because if we're looking for a minimum, then why would it make sense to include that maximum? We've already done the analysis back here that we get a relative max at x equals 3. So that means at x equals 3, that's a relative maximum. That's going to be out of the running for a minimum. So I'm going to go ahead and just cross this one out. And if you want to have an explanation in here, you can say something along the lines of, this is a relative max, which is the reason we're not going to calculate it. We do want to calculate all the other 3, though. So change is always going to be the integral. So I'm going to do 0 plus the integral between, oh, I have to be careful here. Our integral does not start at 0. Remember, I told you that was going to be tricky. Our integral up here is going to start at -3. So all of our integrals are going to look like that. We're going to have the integral of -3 to -5. This is going to be plus the integral from -3 to -4. And lastly, we're going to have plus the integral from -3 to +4. And we should have an f of t dt in all of these. F of t dt, f of t dt, and f of t dt. Okay, so we have to be careful with these first two because our bounds are not in the correct order. Normally it should go -5 to 3. These should be backwards. They are backwards. They should go from a lesser value to a more positive value, and they're backwards. So we need to rewrite this and say this is really the same thing as negative integral from -5 to -3 of f of t dt. And same thing down here. This is really equal to negative the bounds from -4 to -3 f of t dt. And I have no initial condition to do, so we're just going to find a bunch of areas here. So let's get our laser pointer out. Okay, so first let's do between -5 and -3. -5 to -3. What's cool here, check this out. So if I draw a line to this point, and again, I'm doing from -5 to -3. Notice how both of these areas here look the same, and if they look the same, they are the same. Whenever you're looking at these graphs, they cancel each other out. Remember, we have a negative area and a positive area. They cancel each other out, and we're left with 0. So over here, this is going to be equal to 0 plus 0, which is 0. Again, why am I saying 0 plus 0? Because we had this initial condition of 0, and that integral was 0. So nothing to do there. This one is going to be a little bit more engaging because we have -4 to -3, and we won't forget about that negative also. But between -4 and -3, coming back up to the graph, means I'm going from this spot to this spot, which means that I'm only asking for the area of this triangle. So finding the area of that triangle, notice that we have a width here of 1, a height of 2. So if I were to kind of make this into a rectangle, it would be 2 by 1. Half of that is just 1, so we have an area of 1. And it is positive, it is up above the x-axis, so it should normally be positive, but don't forget we have this negative, so it's going to be -1. So over here I'm going to write this is going to be equal to -1. And finally, we have our integral that goes basically the whole thing from -3 to 4. Let's go ahead and find that. So from -3, starting from right here, all the way to 4, my gosh, that's a lot of different things. So we did all this part. We need to just do this piece, and that piece as well. All right, so the way that I'm going to divide this up is I'm going to go ahead and cut right here, make that into a straight line, and there's this end line that I'm noticing immediately that we have, I can use the highlighter tool. This is pretty cool. I have, whoa, that is way too big though. I have this area right here and this area down here. Those areas are going to cancel each other out. So you can go ahead and just kind of cross this off, cross. They are the same area. That means I'm just left with this semicircle that I have to deal with. So how do I do that? And do you really need to do it? I don't think so, but let's just do it just in case. So we have a rectangle, and then I'm going to subtract a semicircle. And that will give us our shape that we need, right? The shape that we need is this shape right here. Not the best artist, but I think you get the point. So the area of the rectangle is 2 by 1, which is 2. And this circle, if I had continued the circle into an actual, oh my god, I'm so bad at drawing circles. That circle would have a radius here of 1, and I'm just using pi r squared here. So this is going to be pi r squared, but it's half of a circle, so over 2. Remember that r is 1, I just said that. R squared means 1 squared. 1 squared is 1. 1 times pi is pi. Pi over 2 is pi over 2. So this reduces to just pi over 2. So our final answer here is going to be 2 minus pi over 2. Okay, so if I fill that into our table, I have, this is going to be, what did I just say? 2 minus pi over 2, I think I just said. 2 minus pi over 2. Oh, but I have to be careful because we have to get all of this other area as well. Okay, so, okay, I'm going to forget this if I don't write it down. So I'm going to give myself some room right here because I have some other numbers to write. But I do have this 2 minus pi over 2 as well. Okay, I do need all of this other area because remember that our integral did start all the way at -3, and I need to get all of this area first. So I have 1 plus 3, which is 4, plus 1.5 is 5.5. So I'm going to come over here and say this is going to be equal to 5.5 plus all of that. And I can move that a little bit closer, make it look organized. And that's just going to be 7.5 minus pi over 2. 7.5 minus pi over 2. And that seems, wait, I feel like there's a mistake that I made. I want to double check this. Why did I say 5.5? Okay, just double checking. Oh my gosh, I see my mistake right now. If you found it as well, then you can log it. I was being silly. I was like, something is irking me. The integral starts here at -3. Why did I say the integral starts here at -4? That doesn't make sense. Okay, that one, we do not include that one. We only include these areas first, which adds up to 4.5, not 5.5. So, sorry about that. That means this is a 4, and that's going to turn that into a 6. 4 and a 6. And cool. Well, I'll tell you this. 6.5 is a big number in comparison to pi over 2 because pi is basically 3. So pi over 2 is basically 1.5. 6.5 minus 1.5 is around 5. So which number is bigger? Again, we're after the, I guess we're after the minimum. So which number is smaller? -1, 0, or about 4? And hopefully you will clearly answer, yes, -1 is the smallest value that we have. So write out your full conclusion. I think I have room down here. I'll come down here and say, I should do a capital letter for the beginning of my sentence. Oh my gosh, I'm just really bad at handwriting right now. The absolute minimum is at x equals -4. With a value of -1. Cool. And I know that the problem only asks for the actual value. You'll read here. It doesn't care where it happened, but I'm answering both because sometimes they ask for both, sometimes they ask for one. Let's see, will this turn into a nice rectangle? Hey, check it out. All right, that one was a long one, but we're almost there for part D. Find all values at which the graph of G has a point of inflection. All right, so speed sheet time. What is an inflection point? And it's a G inflection point, not an F inflection point. So what is a G? I don't know why I'm writing out inflection point. We've been abbreviating that as IP for inflection point. The definition of a G inflection point is where you have a G double prime sign change. And we need to interpret that definition now. So we know that G prime is F. So that means, and here's my logic. If G prime is equal to F, then if I take the derivative of the left and the right, then I'll get G double prime, because I took the derivative of the left. Now take the derivative of the right is equal to F prime. So in terms of this is really F prime. Sign change. And now you get to ask yourself the question, on a graph of F, remember this up here was a graph of F, right? On a graph of F, what is F prime? Is it height, slope, or concavity? And F prime is slope. So the final interpretation here. And again, you don't have to write this last one down, but it is helpful for our notes. I'm really after a slope sign change. So we're going to come up here and look wherever we have a slope that changes its sign. So notice that you don't include the endpoint. So the slope is positive, 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 and boop, all of a sudden the slope is negative. So the first inflection point happens here at x is equal to -3. Slope is negative, negative, negative. Does it change now? Well, at this point, it was negative, and now it's negative again. So it has not changed slope. It's still negative into negative, 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 and then, oop, all of a sudden we turn into positive. So at x is equal to 1, we switch from a negative slope to a positive slope. So we're positive, 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 and then boop, right here at this 2, then we switch from a positive slope to a negative slope. And it stays negative for the rest of it. So once again, slope change 1, 2, 3 different times at -3, 1, and 2. So we'll come down here and we'll say we have a G inflection point at x is equal to, I've already forgotten them. What did I say? -3, 1, 2, right? -3, 1, and 2. Why? It's because that's where you have a G double prime sign change. The definition, your speed sheet definition will always be your reasoning. And that's it. And we can go ahead and box that. And for number 4, again, no calculator. We have a bunch of piecewise linear functions. All right, let's read our function, or read our question. We have a continuous function, g of 2 is equal to 5. That is really weird, but the way that I'm interpreting that is this is kind of like the start condition. And the start condition basically tells us that we are going to have 5 plus the integral from 2 to some number. 2 is that start time, and 5 is the initial amount. And moving forward, this is a graph of g prime, the derivative of g, which is shown above. Okay, so far so good. Let's do part A. Find the x-coordinate of all the points of inflection. So it's a good thing to know what are inflection points. And we're talking about g here because it tells us it's g of x. So the question that I'm asking now is, what is, and I need to move this iPad back a little bit, what is g inflection point? What is that definition, that speed sheet definition? And hopefully you know that I can zoom in a little bit more to make sure that my handwriting looks really neat. That is a G double prime sign change. And then we need to know on a graph of G prime, it tells us that we have a graph of G prime. What is G double prime in terms of G prime? G double prime on a graph of G prime is slope. So I'm going to change this now to slope sign change. Okay, and then we're going to look at our graph. So we have this positive slope, positive changes to positive, so there's no real change here. We have this positive slope, which now changes to a negative slope. So we do have a sign change in terms of the slope here at x is equal to 1 from a positive to a negative. Then negative, 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 and then right here it switches from a negative slope to a positive slope. So we have now 2 of these points that we change the slope. So one of them was at 4, one of them was at 1. So we'll say that that happens at x is equal to, what did I just say, 1 and 4, 1 and 4, and our rationale, we're going to put it again, even though we've already put it once, it's because we already have a G double prime sign change. And that's all we need. I'll go ahead and box it so that the AP grader can find it easier. Slick. All right. B, find the absolute maximum on that whole interval. Justify your answer. So again, you're probably getting used to hearing this, but whenever you see absolute means table. And yet again, we have no calculator, so it's a little bit annoying, but we have to do that. So let's go ahead and first make our table. So I want a straight line right here. We'll have a line. How long should that line be? But I could make it a little bit longer. I could make it come down right about there. And that table's looking pretty great. So we have x values. So I'll say these are our x values, and then we're going to have our start plus our change, and that will be equal to our end, which we're after. again, I'm going to underline the word max here, and maybe I can make that a little bit better. Max, whatever. We always need to have the start and end, this -3 and 7, we need to include in our table. So I'm going to have -3 and 7 automatically included. And then from there, we need to find critical values. And even better, we want to find relative extremums. Again, everything that comes in here is going to be a G relative extremum. So the definition of a relative extremum would be handy to have. So a G relative extremum is where you have a G prime sign change. And put like a colon here to let you know that that is the definition. And on a graph of G prime, notice that this does up here say graph of G prime. On a graph of G prime, what is G prime? G prime is height. So I'm looking for a height sign change. So let's list all those values. First, we have a height that is negative and then positive, and that happens right here. Essentially, another way of interpreting this is, where do I have an x-intercept, where it actually goes through the x-intercept? Because if it came down and then turned around, that wouldn't be a relative extremum. Crosses 1, 2, 3 times. So I'm going to list all those values at -1, 2, and 6. -1, 2, and 6. So -1, 2, and 6. But here's the thing, you don't have to do all of them because there's a cool analytical way to exclude doing those. Remember that we're after a maximum, and the definition of an F relative maximum is where it's a sign change, and I'm kind of like adding on to the definitions down here. It's a sign change from a positive to a negative. That would be a relative max. And you need to be a relative max in order to be an absolute max. If you're a relative minimum, you can't be a max. So notice that in this first example, this first time that you have a change, we go from a negative height to a positive height, which is the definition of a minimum. So I can even label this on the graph permanently instead of with the laser pointer here. This spot right here is a G relative minimum, which is not going to be a maximum. And same thing over here. This spot right here is going to be a G relative minimum, which cannot be a max. The only thing that we do need to include is this spot right here, which is going to be a G relative maximum, which has the potential to be an absolute maximum. So which ones do we exclude? -1 and 6. So I'm going to do like a little wavy line through -1 and 6. And again, my rationale was I'll do it in a different color to make it pop out. That was a relative, maybe I don't want to draw it on top of that. If I'm very careful, I can exclude those, yeah. So that was a relative minimum. That's also a relative minimum, so I'm going to exclude those. All right, now we actually have to find those table values. So notice that I'm using that start condition up here, that I'm starting the integral at 2, and I'm starting with a value of 5, but that is all just summarized right here. So it's going to be 5 plus that integral. That's kind of what I'm copying down over and over again. So this is going to be 5 for the start condition, 5 for the start condition, 5 for the start condition. And the integral is always going to go from 2 to whatever our value is. So our integral is going to go from 2 to that -3, which is backwards, which we'll fix in a sec. This is going to go from 2 to 2, which means we don't really have to worry about it. And finally, this is going to be the integral from 2 to 7. All right, so what's going to go on the inside here? It's G prime, because you're taking the antiderivative or the integral of this graph. We're finding area under the graph for all of these values. So I'll go ahead and finish this by saying G prime of x dx is the formal way that I should be doing this. G prime of x dx and G prime of x. Ooh, I do want it to look kind of nice. I would like to keep this as a key for the future. G prime of x dx. So as I said, this first value up here is backwards. It should go from -3 to 2, so these two need to be switched. And you're allowed to switch them if you do this following. I'm going to change the color here. This is really going to be the integral between -3 and 2 of G prime of x dx. But in order to do that, we're going to change this plus sign into a negative sign. So I'm going to come down here and say minus that. Cool. Everything is set up. I just need to find a bunch of areas now. So first up, what's the area between -3 and 2 on our graph? So between -3 and 2, notice that we're going to have our bound start here at -3, and it's going to end at 2. So just keep a reminder to yourself. It's going like, basically I'm doing this shape and this shape. So I think I'm going to also divide it up like this. So I'm going to have 2 different triangles. That'll make it a little bit easier. All right, so this first triangle has a base of 2, and it has a height here of 1, 2, 3, 4. So 2 times 4 is 8, but it's a triangle, so half of 8 is going to be 4. And not only is it 4, but it's a -4 because it's below the x-axis. Next we have this triangle right here, which is normally this rectangle. That rectangle is 2 by 1, which is 2, but because it's a triangle, it's half of 2, which is just 1. Oh, I want to write that with a pen. And finally we have our triangle over here. That triangle is made out of half of this square. That square is 1 by 1. 1 times 1 is 1, but it's half of that because it's a triangle, so this is going to be an area of 1/2. So I'm going to say 1/2. And those are both above the x-axis, so they are positive. All right, adding all 3 of those together, -4 and 1 is a -3. -3 and the 1/2 is going to be -2.5. So maybe I should show my work a little bit more. So let's do it like this. 5 plus the -4 plus, what was it, the 1 plus 1/2. Those are all the operations that I'm doing in my head, but I want to make sure that you guys can follow that. In fact, it's kind of easier if you do these 3 first, actually. So what do we have? We have 5 and 1 is 6. 6 minus 4 is 2. 2 plus 1/2 is 2.5. So I can say that's 2.5. Oh, wait a second. See, I already made a mistake. I forgot that all of those are going to be negative. So what I need to do is I need to grab all of these, move them over here, and say there's a negative that's being distributed into these values. So I do need to find that first. So what do we have? We have 5 minus, okay, let's go ahead and figure these out. So -4 and 1 again is -3. That's going to be -2.5. So I'm going to have a double negative here. -2, I'm going to say 2.5. And whenever I have a double negative, that turns into, whoa, I double tapped there by accident. Whoa, sorry, that I'm still getting used to the iPad. This is going to be equal to 7.5. Cool. Now we need, we don't need to find the area, because whenever you have the same bounds, 2 and 2, that means there is no area and you have no bounds to go for. So you basically ignore that and you just get 5. So this is over here is just going to be 5. And so far, in terms of who's winning, 7.5 is winning because we're trying to find that maximum value, and 7.5 is bigger than 5. Moving on, we need to find the area between 2 and 7, which is a lot. So between 2 and 7. So I'm starting from here at 2, and I'm going all the way here to 7. So I have triangle and triangle, those 2 triangles. And some people might think that you need to divide this triangle in half, but that is not the case, because as long as you have a base and a height, we have a height, we have a base, we can multiply those 2 dimensions together. So, and even cooler is to think about it like you have a rectangle here, and that rectangle is 2 times 4, right? Because it's 1, 2, 3, 4. Cool. So 4 times 2 is 8. Half of 8 is 4, which means our area in here is -4 because it's below the x-axis, so it's negative. And finally, we do have to kind of have a line over here. Good enough. And that's, I mean, they look the same. This triangle look the same, and indeed, you can just eyeball and be like, oh, that must also have an area of 1/2. Showing my work a little bit, so I have a -4 and 1/2. So we have that 5 as the initial condition, -4 plus 1/2, and that comes out to 1.5. So I'll say that's just 1.5. 1.5. All right, now it's just who's the biggest? Maximum, right? Biggest is 7.5, so we want to write that conclusion all the way out. We'll somewhere over here say that the absolute max happens at, what was the x coordinate? 2. At x is equal to 2 with a value of Why did I say 2? Oh my god. Okay. Our absolute maximum is not 2. It was not that one. It was this one at -3. I apologize. All right. Go back and fix that. X is equal to -3 with a value of 7.5. 7.5. Cool. And that's all there is to that. So we're going to move on to part C, which is really tricky. And in fact, I'm having to re-record this because I made a silly mistake. I thought that this was a g prime of x, but you are asked to do g prime of x down below here. So these two are going to be completely different answers. This is kind of the easier one. This is the harder one that requires you to kind of have the table values from part B correct. So if you didn't get part B correct, you're probably not going to get part C correct. So first, let's start with a speechy definition of average rate of change. So the average rate of change here is defined as, okay, so if I'm talking about G here, I'm not going to use F, I'm going to say G. So I'm going to say G of the second one usually minus G of the first one, all divided by those B minus A values. And my line is a little bit too long, so I'm going to erase a little bit of that. Cool. So for us, all I have to do is plug in what is A and what is B. I'm going to go ahead and call -3 my A and 7 my B. You could reverse those and you'll still get the same answer, by the way. So that means I'm going to do G of 7 minus G of -3. All of this is going to be divided by 7 minus a -3, double negative there, but just remember that you have to worry about that. So this is the hard part. What is G of 7? And you might first think, like I did before I re-recorded this, G of 7, it tells you right here, right? That's G of 7. G of 7 is 1. That's G prime of 7. G prime of 7 is 1. What is G of 7? Well, G of 7 is this value right here. We're plugging in 7, and G of 7 is, and it spits out your final answer over here, is 1.5. That was the tricky bit. So I'm going to come back over here and say this is equal to 1.5 minus, okay, what is G of -3? And just like before, we plugged in -3 for our x value up here, and then what value do we get out? A 7.5. So 1.5 minus 7.5, all of this is going to be divided by 7 plus 3. Again, when you have a double negative, it really means plus. And here at the top, the 0.5s are going to cancel each other out. 1 minus 7 is -6. And I'm realizing that A and B are kind of in the way. Oh, do you know what I could have done? Is there an undo button on here? There is. Here, check this out. This is what I should have done. Grab you, throw you up here. That's smarter. And now I have room to write what I need to do. So this is going to be a -6 divided by 10. And I can reduce that to a -3 over 5. And there's no graphical interpretation of this because we're kind of going with the antiderivative here, but it's good enough. Cool. Now we can go on to the easier to understand question, find the average rate of g prime of x, because that just comes from the graph. In fact, there's a geometric way to think about the average rate of change when you have the function that you're looking for graphed. We have a graph of g prime, so there is a geometric meaning for the average rate of change of that g prime, and let me show it to you right now. Because this is the g prime that we're talking about, this is a graph of it. If I'm talking about the start to the end, which I am because it's going from -3 to 7, then the average rate of change is from the start to the end. Connect those with a straight line, and it's asking what is the slope of this line. If you tell me the slope of that line, that is the average rate of change. But again, you don't have to know that. That's helpful to know in some cases, not in this case. You just have to go again with your speed sheet. What is the speed sheet definition of average? That's supposed to be a V. Average is, okay, I'm not talking about G anymore, I'm talking about G prime. So G prime of B minus G prime of A, all of this divided by B minus A. And it's the same values as before, 7 and -3. So I'm going to do G prime of 7 minus G prime of -3. And that's all going to be divided by 7 minus a -3, double negative again. And now we have the easier question to answer because we can't get it wrong if we got part B incorrect. G prime of -7 comes from the graph, right? So G prime, this is a graph of G prime, first of all, of 7 spits out the value of 1. It has this height over here of 1, right? And same thing over here, G prime of -3 is -4. So I get 1 and then -4. So I'm going to come down here and say this is 1 minus, and then that's going to be a -4, a double negative on the top, double negative on the bottom. In fact, I'm going to go ahead and leave the double negative just because it looks nice to have them both there at the same time. That's going to turn into 1 plus 5, 7 plus 3. Why did I say 1 plus 5? 1 plus 4, Mr. Sindel. There we go. I'm just randomly changing my numbers. 1 plus 4 is 5. Maybe my brain was in overdrive. I saw a few steps ahead. 5 over 10. 5 over 10 is 1/2. Okay, you're not done. There's a lot that's being asked in part D. All we did was we did that first part. Find the average rate of change. Check. Okay, let's read the rest of this. Does the mean value theorem applied on the interval guarantee a value of C in between -3 and 7, which is what we found our bounds for that first part, such that if I take the derivative of G prime and get G double prime is equal to the average rate of change? It's basically asking, does mean value theorem apply? Because this is the exact phrasing of the mean value theorem. But remember, there are a set of requirements for mean value theorem, and there's only one requirement really. It's differentiable. And differentiable means there are no sharp corners, no vertical tangents, and no, what's the other one that I'm thinking of? Oh man, I'm blanking on it right now. You guys are shouting at the computer and I don't hear you, I'm sorry. So there's vertical tangents, oh, and discontinuities, right? It's all those 4 that we know. So just like a jump discontinuity and stuff like that. Cool, so those are the 3 that we have to worry about. And hey, sharp corners is one of the things I listed, and that looks pretty sharp, that looks pretty sharp, that looks pretty sharp. Each of those 3 points that I've listed are not differentiable. So because we have at least 1 or more points that are not differentiable, we can't use the mean value theorem. That's exactly the answer to this question. So does mean value theorem guarantee value? And we can answer no. MVT does not. Does not guarantee. I forgot how to spell guarantee for a sec. There it is, guarantee. Let's just copy that down. G-U-A-R-E. Oh my God, I can't even copy correctly. I'm so bad. Guarantee. Anything. Why? Because there is at least 1 point on that interval, and I'll just rewrite that interval, on -3 is less than x is less than 7, where, I'll just come down to the next line at this point, where the function is not differentiable. There might have been a more concise way of writing that, but that's how I'm going to answer it. You need something along those lines. All right, number 5 is also no calculator. And whenever they give you a table, you automatically think I'm going to be using some sort of Riemann sum. And oh yeah, and then check this out. So 0 to 4 is 4, 4, 4, 4. All of these intervals are 4, and it tells you that it's recorded every 4 minutes. But that does make me happy. That means since we don't have a calculator, I'll be able to factor out that 4 to make my calculations a little bit faster. I don't think there's super important information in that first body paragraph. So just moving on to part A, trying to estimate an instantaneous rate. We're trying to estimate a capital H prime, because capital H, right? So H prime of 10, how do we do that? Well, notice that 10 is in between 8 and 12. It should be somewhere right about here. So I'm going to use these 2 values and these 2 values, all 4 of those, to estimate H prime of 10. So the formal way of showing how to do that, you say that H, capital H prime of 10 is approximated by, so you have the little approximation symbol, and then you'll do capital H of, the one on the right, which is going to be 12. H of 12 minus capital H of 8. And by the way, I am being way too formal about this. Normally I wouldn't write all of this work. I would just plug in what they are exactly. but I want to show in the answer key and in the video where I'm getting these numbers from. And that's all going to be divided by 12 minus 8. All right, well, what is h of 12? H of 12 is that table value. H of 12 goes to 80, so I'm going to plug in 80 for this h of 12. So I'm going to say that this is 80 minus h of 8 is 73. All of this is going to be divided by 4, because 12 minus 8 is 4. And 80 minus 73 is 7, so we get 7/4. So we're not done. We got the answer, but read the question again. We have to indicate units of measure, otherwise we're going to lose a point. So 7/4 what? And because we're taking the derivative, we're adding on a time. We're dividing by a time, essentially. So we're already in degrees Celsius, but now we're going to be degrees Celsius per minute. So this is going to be degrees Celsius per minute. Cool. Moving on to part B. Write an integral expression for the average temperature. Okay, so whenever I see these words average, I automatically think of that speechy definition of what is average. And let me write that down as well for you. It's a little bit different than the previous average that I gave you. Because I think I told you that average was like f of b minus f of a all over b minus a. I mean, that is true, but it really, the roots of all of that comes from taking an integral. The average of anything is going to be 1 over b minus a times the integral from a to b of that anything. So maybe a way of saying that is if I move average over here and I say average of something. Can I call that S? I'll just leave it blank. Average of something is the integral of that something. You kind of copy down that same value. So in my highlighter tool, this and this, they are the same something. So if we're talking about temperature, then I'm going to, in the place of this yellow highlighting tool, I'm going to say that is temperature. So for us, it's going to be 1 over, okay, what are my B and A's? My bounds are going to be between, let me read the question, between, it says time equals 0 and time is equal to 16. So it's going to be between 0 and 16. So integral from 0 to 16, which means I have 16 minus 0 over here for my time. And it's talking about temperature. It wants to know the average temperature. So I'm going to plug in temperature. When I do that, I'm just going to say h of t. H of t is temperature, right? It tells you that up here, h of t is just temperature. So I'll just say capital H of t, dt. Cool. And that's all it's asking for. It just told us to write that expression. Done. Keep reading the question. Okay, now that we've written that, estimate the average temperature. Given a left Riemann sum. Okay, so this is important. It's a left Riemann sum. Remember the shape for left Riemann sum. Your speech sheet definition for a left Riemann sum looks like this, where you have kind of like a pot boiling or something like that, or a Tetris piece with the piece sticking out on the left. 4 subintervals of equal length. That's pretty straightforward. So let's go ahead and do that. I'm going to say, I've already written out my integral expression, so I'm going to say, okay, now I'm going to approximate that with the following. So I think the easiest way to show this is, can I try highlighter? I have never used this before. So I'm going to do that shape right there, and that's going to be 4 minus 0 times 65. So I'll write that over here, and that's going to be 4 minus 0 times 65 plus, and then the next shape I'm going to do with a different highlighter color. Oop, that's an eraser, which is going to be this shape right here. I don't know if that's easy to see or not, which is 8 minus 4 times 68. 8 minus 4 times 68. Then the next highlighted color is here, 12 minus 8 times 73, plus 12 minus 8 times, what did I just say? 73, I think. I hope so. 73. I'm really bad at remembering numbers. Plus, and finally we have, I don't know, so I'm going to go back to the yellow or orange color. This thing, 16 times 12, or 16 minus 12, and then times 80. So it's going to be 16 minus 12, and that's going to be multiplied by 80. Cool. And then you'll note that each of these values in here, and I can I'll just use the laser pointer. These values are all going to be 4. And that's what I meant by factoring out the 4. So another way of rewriting this is exactly equal to 4 times the quantity of 65 plus 68 plus 73 plus 80. It's a little bit faster way of doing that. All right, are there any good pairings here? Nothing that makes like an even 10. So I'm just gonna kind of brute force this. Let's do these two first. Why not? So 65 and 68 is 133, and then these two together gives you 153, and adding those two together gives you 286. Why did I write 283 then? 286. And that's going to be, I'm like, that's way too big of a number. And it's because I forgot to do my divided by 16, right? So in order to make this static answer key correct, and I apologize if you're following the video exactly, I need to put the 1/16 out here. In fact, hold on, I'm going to grab everything. So I'm going to grab all of you, move it over a little bit so I can write the 1/16 out in front. So I'm going to say 1/16 times all of that. And that means I need a 1/16 times that, which means my answer is going to be, oh, and check this out. So notice that the 4 and 16 are going to cross cancel, and that's going to be left with just 1/4. So their answer here is going to be 286/4. And that can be reduced because I can divide both top and bottom by 2. So it's going to be 143/2. And I mean, I can divide by 2 pretty easily. That's basically 71.5. So again, you can leave it as a fraction, just totally fine. But because I know how to divide by 2 and make it as a decimal, I'm going to do that. 71.5. Either way, you'll get the points for that. Now, do we answer everything? Let's go back to the reader question. So left Riemann sum, there are 4 intervals. Yeah, check it out, 4. 1, 2, 3, 4. And show the computations. I definitely showed all of my work, and I did get 71.5 correctly. Cool. Moving on. Is our approximation that we just did, that 71.5, an underestimate or overestimate? Okay, so I'll be honest with you guys. I've been teaching AP Calculus for a long time, and I've never memorized the definition. I always have to redraw this for myself. So what's happening here? In our table, notice that each of these values is going up. 65 to 68, you're adding, you're going up, you're going up, you're going up. It's monotonically increasing is the technical way of saying that, but the simple way of saying it is it's going up. So let me draw a function that is going up. This is me just giving a quick sketch. And it doesn't matter if my sketch is concave down or concave up, you'll get the same answer. And just to prove it to you, I'm going to do one for both. Just make sure that your function is constantly going up, and then do a left Riemann sum. So left Riemann sum means you use the leftmost point. That means I'm using this leftmost point and then drawing a height out to the right. Using the leftmost point and drawing a height out to the right. Using the leftmost point, drawing out to the right. And I think by this point you can kind of get the gist, right? Drawing out to the right. No matter what I do, there's always going to be this area that I'm not accumulating, I'm not accounting for. That's what I'm looking for, which means we're going to be an under approximation. And notice that it doesn't change depending on the concavity. I know that students always are worried about, is it concave up, concave down? It doesn't matter. It's just the fact that it's increasing. Look, even though that this one is concave up versus the last one that was concave down, you're still doing a left Riemann sum, which means you're using that leftmost point, and we're still getting this area that we're not accounting for, all of these areas here. So our simple answer is it's an under approximation because we should have been including those areas. So let's say that in words. We'll say our approximation is, I was just trying to think, are we past tense or present tense? And it's saying is, so I'm going to just copy down is an under approximation. And you had to have these two key things because I would say the function, I was going to say it is, but I should refer to what it is because our function, which is called capital H, I believe, yeah, capital H of t, because capital H of t is increasing, that's the first half, and the second half is, it's a left Riemann sum. And we have do I have enough room here? I do, okay. A left Riemann sum. Did I even spell Riemann correctly? I think they spelled it for us somewhere, right? Yeah, so there it is, Riemann. I think I spelled it right. Yay! All right, that's all you have to say. Cool. And on to part, wait, did we answer all the question? I always make the mistake. Give a reason for your answer. Okay, our reason for answer, boom, right there. So far, so good. On to part D. Are the data in the table consistent with, or do they contradict the claim that the temperature in the oven is increasing at an increasing rate? And give a reason. Okay, so first of all, it's definitely increasing. Like the first part, there's no debate. I just said it up here, right? It's increasing, increasing. But what about the rate at which it's increasing? It's asking about the second derivative. It already knows, yeah, the first derivative is positive. It's increasing. But what about the second derivative? And this is where you have to do table calculus. I don't actually know the term for this, but it's where you write out your values again, and then you do a different type of analysis that I don't frequently teach in my class. So if you're paying attention to the video, good for you. You're going to learn it. I'm going to go ahead and rewrite these values, the 65 all the way through 90 again, but I'm going to write them vertically instead of horizontally as was given to us in the table. So our values, once again, are 65, and I'm noticing that my handwriting is getting worse when I'm zoomed out, so I'm going to zoom back in. That way when I zoom out, it looks impressive. 65, 68, then it was 73, 80, 90. Okay, so whenever you look at how much is being added to, or if you're I think a better way to think about this is, what is this number minus this number? What is that difference? And I'm going to call that the first, whoa, that's not how you spell first. The first difference. The first difference represents the first derivative when you're talking about a table. So I'm going to say, okay, to get from 65 to 68, I had to do 68 minus 65, which is a positive 3. To get the next value, I had to add 5. Another way to think about that is, what is 73 minus 68? What is 80 minus 73? Well, that's a positive 7. What is 90 minus 80? That's a positive 10. Cool. So the first difference is the equivalent of this is the same thing as the first derivative. So that means that the second difference is the equivalent of the second derivative, and that's how you solve this problem. So I'm going to do the same thing again. How did I get from 3 to 5? Well, I had to add 2. Another way of thinking about that is, what is 5 minus 3? Positive 2. What is 7 minus 5? Positive 2. What is 10 minus 7? It's a positive 3. And that column there, I'm going to go ahead and label that my second difference, and that is synonymous with the second derivative. That's the second derivative. Cool. So, and that's what it's asking for, right? Because in our problem, we already knew it was increasing. We knew all these values were going to be positive, but it's asking about the second derivative. Is that increasing? That's the second derivative. So are these values all positive? And indeed they are. So the rationale for this, again, I wish that there was a more concise way of doing this. Maybe after teaching a few more years, I'll have a better way of answering this. I have a very lengthy response to this. So give a reason. I mean, having that table is pretty good so far, but even if I didn't have this table, I could answer the following. So I'll say the first differences are positive, and I guess I'll just say, which means, whoa, didn't mean to go that far, which means, whoop, I hit that button by accident on the iPad, the home button. The first differences are positive, which means the function is increasing. And if you want to be like, you don't have to go overboard, but I'm going to for the answer key. The first derivative is positive. And you also want to say the second differences are positive. And that means, well, that's kind of a bad W. I'm going to go ahead and try that again. Which means the function is increasing. That was a bad G. Again, I want to make it look kind of nice. Increasing at an increasing rate. And I'll put in parentheses, which you don't need to do, but I'm being overboard in terms of my analysis. The second derivative is positive. And I have to be careful with this because it kind of sounds like I'm arguing that all of the first derivative is positive and all of the second derivative is positive, but I don't know that because it's a table. It's incomplete data. So as far as I can tell, they look to be positive, but if they randomly said, oh, you know what, they added a value, which means that we randomly have a negative value right here, which messes up all of that and all of that. Again, we have incomplete data. So far, the data is consistent with it, and I like that word that they're using. Is it consistent? And it is. They could add data that would make it inconsistent, but for now, it is consistent. And I apologize for that lengthy response, but that's the way that you do your analysis. And we zoom out so we can see it. Number 6, and this is, I think, the last time that we don't have a calculator for a bit. I think number 7, we do have a calculator. Another table, and like, yes, it seems like it's a pretty constant 3, 3, 3, 3. That'll be nice, I hope. And yeah, this is kind of an older one, 1999. And you'll notice it kind of just immediately jumps in with a Riemann sum. It doesn't even buy a Stinner first. A little bit strange. Anything important in the first paragraph? Nope. All right. Well, let's just go ahead and calculate a midpoint Riemann sum. Remember the pattern for midpoint Riemann sum? I'm going to try to use this calculator, or this highlighter. It's going to be using kind of this weird pattern of having these two 6 minus 0, and then you're going to multiply by 10.4, and then that pattern is going to go throughout the rest of this. And one thing that I always have to double check, because I've made this mistake a few different times, is when it's asking you the interval, make sure it's doing the entire interval. There's so many times that I've done like an interval where it's asking me, oh, what is it between 3 and 21? And I've done it from 0 to 24 by accident. Make sure you're doing the right one. We are doing 0 to 24, so I am using the 0 and 24. But just double check that whenever you're doing these Riemann sums. It's an easy mistake to make. And then we got to do some interpretation after we do that. I'm reading ahead for the problem, but let's go ahead and calculate that midpoint Riemann sum. So I am going to say, I'm going to write it out in full, and then I'm going to show you a little bit of a shortcut. So I'm going to do 6 minus 0. Again, 6 minus 0, and I'm going to multiply that by 10.4. So I'm going to say this is going to be, do I want to write out what I'm doing? I'm just going to go for it. 6 minus 0, and then I'm going to multiply that by 10.4. Man, I really wish I had a calculator. Plus, and then it's going to be 12 minus 6 times 11.2 plus 18 minus 12. That's going to be multiplied by 11.3 plus, and finally, 24 minus 18 in parentheses times 10.2. Okay, and the way that what I do when I'm at this step is I just immediately jump down to here and I factor out a 6. Each of these is 6, right? That's a 6, that's a 6. All 4 of those are 6s. I'm going to factor out that 6 right now. So this is going to be 6 times the quantity of, and then you're just left with the remaining numbers like 10.4, 11.2, all of those, right? So I can now say that this is going to be 10.4 plus 11.2 plus 11.3 plus 10.2. Is there a nice way of doing these? I'm trying to see if any of them add up to like a 10 or something. And no, I'm just gonna go for it again. Okay, 10.4 plus 11.2, that's gonna be 21.6. 21.6. These two add together is a 21.5. 21.5, and then those two added together gives us a 43.1. 43.1, and I still need to multiply by 6 here, and I think I can do that in my head. Let's see how good I am at math. I see at the 6, and then 6 times 3 is 18, so the decimal point is going to go right here. 18, carry the 1, 6 times 4 is 24, but I'm carrying the 1, so it's 25. 258.6 is what I'm getting, and I think I did that all right. All right, so that's only the first half of the question, so be careful, right? Using correct units, explain the meaning, and then here's the key. In terms of, you need to use this word. If you don't use water flow, you're not doing the right problem. You're not doing it correctly. So first of all, let's just deal with units. If we take the integral, again, it says you're basically taking the integral of r of t. So here's r of t. If we take the integral of that, that means we're getting rid of a per hour, and I'm just left with gallons. So the correct unit here is, this is a unit of gallons. So what does this mean in terms of water flow? And you can say in words. This means, and I can spell, this means from 0 to 24, are we in hours? Yeah, hours. From 0 to 24 hours, there were, and I basically want to say 258.6 gallons, and then I need to somehow say of water flow. Yeah, I'm just going to say 258.6 gallons of water flow. It sounds kind of funky, but I'm using the word water flow. There were 258.6 gallons. Can I fit in of water flow? I'm going to put down here. Of water flow. Yeah, I'm going to go with that. Yeah, I've answered all the parts of the question. Part B. Is there some time where r prime of t is equal to 0? Justify. All right, so you need to go through your catalog of where do I have something that guarantees r primes. And the first thing that I think of is mean value theorem guarantees slopes, and r prime is a slope. So I must be using mean value theorem here, and indeed you are. I'm going to show you the long path, and I'll talk about the shortcut. You need to list out what is mean value theorem. Usually it's f prime of x, but in this case we have an r prime of t. So I'm going to just go ahead and say, yeah, r prime of t. So r prime of t, that instantaneous rate of change needs to be equal to r of b minus r of a all over b minus a. We need to find a t that justifies this. So, and here's the cool thing. We want r prime of t to be 0. It says this r prime of t, that r prime of t, it has to be 0. So I'm going to change this thing to 0, and I'm going to do a little bit of algebraic manipulation. I'm going to say, okay, 0 is equal to, just go ahead and rewrite all of this, r of b minus capital R of a all over b minus a. And then I'm going to multiply both sides by b minus a times b minus a. And yes, that does mean that these two things will cancel each other out. And guess what 0 times anything is? 0. So on my very next line, it's basically as if I ignore that b minus a, right? I can say that 0 is equal to capital R of b minus capital R of a. And finally, I can add a capital R of a to both sides, plus R, maybe I should do this in a different color. I do want to do it in a different color to make it really pop. So I'm going to say plus R of A plus R of A on both sides. And that is going to give us, shwink a line, R of A needs to equal R of B. I'm finicky about my handwriting tonight, aren't I? R of B. Cool. Well, if there's some R of A that's equal to an R of B, then we win. And you should be able to jump here every single time because this question is asked pretty often. I've asked it to you guys a bit. Where do we have a derivative that's set equal to 0? If it's set equal to 0, just find two values that are the same for that bottom half of our table. If any of two of these match, you win. And this is the formal way of proving that you do not need to show. Nothing here needs to be shown and you'll still get the right answer. All right, try to find values. Is there another 9.6? And there is. All right, so automatically we're good. Are there any other duplicates? 10.4, no other 10.4s. 10.8s, no other 10.8s. 11.2s, no other 11.2s. And you can see pretty quickly none of them are going to match except for the 9.6s. And those are done on purpose. So lucky for us, our interval is exactly 0 to 24, but it doesn't necessarily always need to be. What if that 9.6 and 10.8, what if these two are switched? Then we'd say, oh yes, well, between 6 and 24, we can definitely guarantee that we have some derivative that's equal to 0. For us, we just happen to find 0 and 24. So the way that I'll say this is yes, because the question is asking, is there some time? Yes, there is some time. Yes. And just remember, I'm being like super formal now. So it told us that the function was differentiable, which is really important. It's differentiable, which means we have permission to use mean value theorem, but you want to restate that because they want to know, oh, are you allowed to use mean value theorem? Anytime that you want to use a theorem, you got to say, hey, we met the requirements so we can use it. Yes. So we'll say because the function, instead of saying the function, I can even say because capital R, right? Because capital R of t is differentiable, we can use MVT, the mean value theorem. So now that we can use mean value theorem, now I'm going to say since, and then the thing that we discovered is R of what two values? R of 0 and R of 24. Since R of 0 is equal to R of 24, there must be a time in that interval, a time in the interval between 0 and 24, in 0 to 24, such that R prime of t is equal to 0. R prime of t is equal to 0. And that's all you have to say. But again, all of that logic came from over here on the left-hand side, which you don't have to restate because you'll already know that, right? That's all you need to say. Part C. Oh boy, that like whenever I see this function, I'm like, I really, really wish I had a calculator right now. Oh boy. And we need to approximate the average rate of water flow. There's a lot of things going on for this one. The C is going to be worth like a lot of points. There's a lot of things to do here. All right, on our laundry list of things to do, let's first define what is average rate. Yes, it's equal to an average slope, but we don't have that. We just have a function. We just have this thing. So we need to use an integral. So we'll say that the average Q. So the average Q here, average Q of t, is going to be defined as 1 all over b minus a of the integral between a and b of q of t dt. And we need to do that. So I have a feeling that we're going to run out of room. Oh, there's a lot of blank space. I think I'll be fine, but I'm going to just conserve space for now. What is that going to be for us? Because we're doing I'm trying to figure out A and B right now. And I'm noticing it's telling us it's a 24-hour time period, and that's all it's really giving us for the interval. And that makes sense because the table up here is between 0 and 24, so our bounds are between 0 and 24 for the 24-hour time period. So for S, that's going to be 1 over 24 minus 0, integral from bounds from 0 to 24 of, I can't just write Q of t because I have to actually do it, of 1 over 79 times the quantity of 768 plus 23t minus t squared, that thing, dt. And we have to do that by hand. All right, well, let's get started. The first thing that I want to do is I want to bring this outside, because whenever you have a number, this is just a number, right? A constant term. You can always bring constant outside of an integral. So and then the other thing I should do too is do the analysis. Do we need to pay our tax person? And notice that there is no number right here, which is nice, because if there was, then I would have to, I would have a house, and I'd have to find dinner, pay tax person, whatever. We don't have a house. If you don't have a house, you can't pay tax person. You can argue that, oh, well, that is the house of the powerhouse because it's power of 2. Okay, great. Yes, that means that the inner is t and the dinner is 1. You don't have to pay tax person. You never pay tax person if you have a house and inner is 1. And if you don't even have a house, you never pay tax person to begin with. So it's a long-winded way of saying you don't pay tax person for this problem. So don't pay tax person. Let's bring the 1 over 79 out. And I'm not going to multiply those together because I have a feeling that there's going to be some sort of cancellation. Otherwise, this problem is going to be way too gross. So I'm going to take the antiderivative all at the same time. This is going to be equal to 1 over, maybe doing this a little bit too big, 1 over, I'm still doing it the same size, whatever, 24 times 79. Okay, that's the fraction out front. And antiderivative of 768 is 768 t, not x, right? Because we're dealing with t. And I'm trying to make my t's curvy on the bottom so you don't confuse them for plus signs. And then I'm going to add, that is a plus sign, I make it small and not curvy, 23t. So that's going to turn into 23t goes up a power to the power of 2, divide down by that 2. And then finally minus, and this is going to be t goes up a power to the power of 3, divide down by that 3. All right, well, I mean, that wasn't that bad, but we do have to do an evaluation bar between 0 and 24. Okay, so one thing to keep in mind is this constant term over here, I'm totally factoring that out. Like I'm not doing that over and over again. I'm really only doing this definite integral, this 24 and 0, and I'm plugging that into these, and I'm not doing that until the very end because there is too much work. All right, so what do we got here? Well, so I'm going to leave this as, I'm not going to forget about it. I'm going to leave this 24 times 79, and that's as much as I'm going to do for now. And then I'm going to have, oh boy, 768 times 24 plus 23 times 24 squared. My God, that's a big number. And that's all going to be divided by 2. And then minus 24 cubed. Dear gosh, 24 cubed is gigantic. Over 3. Oh, okay, check it out. I'm so glad that we did not multiply these together because check it out. 24, 24, 24. There's a copy of 24 in each of these, and there's a being divided by 24, which means cancel, cancel. That turns into 1, that turns into 2. Lovely. All right, that makes me feel much better. And then I'm going to have to plug in 0 and check it out. Okay, when you plug in 0, this 0 is being plugged into this t, and this t, and that means all that 0, all that 0, all that 0. And just to show my work in my key, I will say, yes, I did do that. That's 0 plus 0 minus 0, which means we don't have to worry about it. Okay, this problem is actually cleaned up really nice. So, as I said before, I'm going to cancel out those 24s. So I'm going to be left with 1 over 79, and that's going to be still multiplied by 768 plus 23 times 24, now to the power of 1, because I got rid of one of the copies here. And I'm going to get rid of one of the copies here, which leaves 24 to the power of 2. So this is going to be minus 24 to the power of 2, don't need parentheses, over 3. Did I forget my over 2 over here? I think I did, yeah. Okay, not too bad. And let's do this by hand. Okay, keep going. Okay, I'm going to cross cancel here. So 24 and 2 is going to cross cancel, and that's going to turn into a 12. And then for this 24 squared over 3, I'm thinking 24 is divisible by 3. So really I can write this as, here, I'm going to go ahead and go to another line. 1 over 79 times 760. I'm trying to use all my bag of tricks to make this as easy as possible. Plus 23 times 12. We'll do that in a sec. Minus, okay, really we have 24 times 24 all over 3, and we can cross cancel one of those. We can say 24 divided by 3 is 8. So really I have 24 times 8, and no division happening. All right, so far so good. And I am kind of running low on room, so let's try to conserve as much space as we can and move that up here. We do need an equal to sign. All right, I'm going to do some math off to the side. Oop, I don't want to change that. I want to change the color. So I have 23 times 12. I'm always thinking, what is the fastest way to do this? And some people are like, just do it the old-fashioned way that I have, and I might just do it. Just as a heads up, the other way that I was thinking about doing was 20 plus 3 over 10 plus 2 and making this cool little box, but I'm not going to do that because I like to vary my strategies to be strong at all of them. So 2 times 3 is 6, 2 times 2, 4. There's a 0 here, 3, 2, and I have to add 6, 7, 2. Okay, so 276. So that means over here I have 1 over 79 times 768 plus that 276 that I just found minus, okay, I need to do 24 times 8. And I'm going to do that kind of the same way. 24 times 8. 24 times 8. 8 times 4 is 32. Carry the 3. 2 times 8 is 16, 17, 18, 19, 192. So this is going to be 192. That's supposed to be a parenthesis, but I can't draw curvy lines right now. And we're really, really close. Okay, what do I want to do first? That 192 does not look fun. Let's go ahead and add those two first numbers first. I'm going to add 768 plus 276, which still seems hard. This is going to be, let's see, the 6 and 8 is going to combine to a 14, carry the 1. I'm holding up a 1 for my hand so I can remember it. 7 plus 6 is going to be 13, plus the carried 1, so that's 14, which again, I'm going to carry another 1. And then 2 plus 7 is 9, but carry the 1 is going to be 10. Oh no, I probably shouldn't have added those two together first, because I still have to subtract 192. And I'm going to go ahead and write the 79 on the bottom for now. And then I have to subtract 192. I don't know if I can do this in my head, guys. I'm going to have to draw it out to the side. So what is 1040? Ooh, that's a bad 4. Even though it's only my scratch work, I don't want it to look too gross. 1044 minus 192. I'm instantly regretting adding those two numbers together first because I have to do so much borrowing. Anyway, this problem, 4 minus 2 is 2. 4 minus 9 you can't do, so I'm going to change that 4 into, I should really change, oh, that's not what I want to do. I want to erase that. I'm going to go ahead and change colors. So 4 is going to change into a 14, which means I have to borrow from here, which I can't borrow from yet. So change that to a 0, change that to a 10, and then borrow from the 10 to become 9. Okay, I'm done all my borrowing. 14 minus 9 is 5. Ooh, don't red, I want black. So that's a 5, and then 9 minus 1 is 8, so 852. So this is going to be 852 over 79. Does 79 go into 852? That'd be kind of cool if it did. I'm trying to think. If it did, it would be like, what would be 79 times 5? Oh no, it has to end with a 2, right? So the only things that end with a 2 when you multiply by 9, you can multiply 7, and that's the only one, right? And 7 times 7 is 49. Oh, maybe. Hold on. I just want to check because this would be really cool if it's simplified. What is 79 times 7? Because if that's 852, that's super cool. So 7 times 9 is, wait a sec. Am I doing this right? My brain is writing 63. I want to end it with a 2, not a 3. So not 7, but an 8. 8 times 9 is 72. 7 times 8 is 56. That's not going to work, is it? Because that's going to be 63. Dang it, that's the only way that we could have ended with a 2. So that didn't work. All right, well, it's always kind of cool to check. That's as far as we can go. Did we even answer the question? Okay, we answered everything except for the last part. We approximated the average rate of flow. It's that gross fraction, but we didn't indicate units of measure. So make sure you answer the complete question. Always come back at the very end. This is something that it took me a long time to learn. Always come back and reread the question. Make sure you answered everything. We did not indicate units of measure. So what did we do? We found the, I mean, that was just water flow, but we wanted to find the average rate of water flow. And the way that I always think about average is it stays with the same units. If I ask you, oh, what's the average temperature outside? You'll tell me it's 28 degrees. You won't change it to like it's 28 degrees per second. That wouldn't make sense. So it's the same unit. So what is the unit of water flow? Because that's going to be our same unit. And did it tell it down here? It did not say it down here. Does it say anything for water flow? Check this out. Rate at which water flows. So water flow is given by R, and R is given in gallons per hour. So we're also going to be in gallons per hour. So come down here. This is going to be gallons per hour. Okay, I definitely want to box up because my work is everywhere, and I want the AP grader / Mr. Sindel to know. Whoa. I guess I picked up my pencil. I was trying to make that cool little box. I definitely want Mr. Sindel / the AP grader to know where my answer ends so they can kind of track what I did. We finally have our calculator question, and the first thing that I notice is that I'm given two equations for rates, one for positive, one for negative. It doesn't even matter which one is which, but you want to plug them both into the calculator. So be careful with your parentheses, especially when you have these giant embedded fractions. Well, not really embedded fractions, but big fractions. So plus 10 divided by, okay, so now that I've hit the divide by, I'm going to put my parentheses, make sure everything stays on the bottom. 1 plus natural log of t plus 1, and parentheses. You don't really need it in parentheses, it can figure that out. And the next function is going to be 12 sine, and then it already had the parentheses for us, so it's going to be t squared, and then that's going to be divided by 47. Cool. And then we might as well do the positive minus the negative. So it does tell us that pumped into is kind of a positive word, and then removed is a negative word. So the way that I'm going to annotate my functions here is I'm going to say that this is the positive function and this is the negative function. And you always, every single time that you have two functions, the first thing you should do, you do the positive minus the negative rate to create a new equation. In fact, I'm not even going to graph these equations. I'm going to hit enter on the equal to sign, enter on the equal to sign, so they don't even graph. I don't think I'll need them. And then finally, I'm going to do vars right, enter 1 minus vars right, enter 2. I'm going to do y1 minus y2, and that's the only thing I'm going to graph. And my interval, my window, is going to be between 0 and 12 because it tells me down here 0 to 12, right? And up there as well. So 0, enter, 12, and then I'm going to do zoom, 0. That'll graph. While that's graphing, let's come in here and figure out what it's asking us for the first question. How many gallons of heating oil are pumped into the tank during that time interval? Okay, so it's purely asking about the positive amount, only talking about into. It's not talking about the overall levels, just how much is going into. It's only talking about the positive rate. So we're only talking about capital H, not capital R. And since H is a rate, we need to take the integral of that rate to get an overall amount. And we don't care about any starting amount. We're just figuring out how much is added. Just take the integral, right? No initial amount. So it's going to be the integral from wherever the start time was. So 0 to 12. Integral is also going to be between 0 and 12. And it's going to be of capital H of t. H of t, dt. And now that I've graphed this, I can get rid of this on the calculator. I can do math 9 0 to 12 of vars right, enter only y1, right, with respect to x, and we get our answer. This should be, yep, 70.571 if I'm rounding correctly. So this is going to be equal to 70.571. And do we need units? It doesn't ask for units, but we should be careful. If we were asked for units, it would have been gallons. So I'm going to go ahead and just put gallons, even though you don't need it. The way that I know it's gallons is whenever you take the integral, you get rid of a time unit. So where does it tell you? It tells you right over here. Oop, come on. Gallons per hour, and when you take the integral, get rid of the per hour, and you just get gallons, right? That's all we need to do for the first part. Let's go ahead and do part B. Is the level of the heating oil in the tank rising or falling? Okay, well, now we're talking about that y3 function that we made. We're doing the positive minus the negative, and that is the overall rate for the entire tank, which is what this question is asking for. The overall oil in the tank, is that going up or down? Well, we're going to compare. Is that that y3 function that we made, is that a positive or negative rate? If it's a positive rate, then it's going up. If it's a negative rate, it's going down. So if I just come over here to my graph, and I can do a trace, actually. Trace at 6 and hit enter. At 6, it seems to be a negative height, therefore it's a negative rate. So I can say, for my actual description of what's going on, I have a y3 function, and that y3 function is h minus r. And I'm plugging in 6, so I'm going to say h of 6 minus capital R of 6 is equal to that negative 2.924 on my graph after I traced it, which is a negative value. So we can now finally answer our question, which is the level of heating oil is falling. And why is that the case? It's because this thing that I just found up here is negative. So I'm just going to rewrite that and say that thing is negative. Is falling because, what are my letters again? H and R. Because H of 6 minus R of 6 is negative, is less than 0. Cool, that's all I need to say. Part C, how many gallons of heating oil are in the tank? Okay, so this is asking for an end amount, the actual number of gallons at the very end of 12 hours. This is going to be a start plus change is equal to end. So I'm going to do start plus change is equal to our end amount. In this case, I do have to be wary of what is our start condition. And I should have annotated up here in the very beginning of the problem. That was bad of me. It contained 125 gallons of heating oil at time is equal to 0. So that's our start amount, and that's our start time. So I'm going to label both of them as start conditions. I mean, starting time is equal to 0. That's kind of a given for this problem, but still, maybe they'll be like, oh, start time is 1 because people were an hour late or something weird like that. I've never seen that, but it could happen. So our start is 125, our starting amount 125, and our integral does start at 0 because that was the other start condition, and we want to end it. It says over here in the problem we're going to end it at time is equal to 12, so that means that this value up here is going to be 12. And what do we want to do? The overall amount of oil, we're going to do, what is it again? It's H minus R, right? So H, capital H of T minus capital R of T, and then that whole thing, quantity times dt. Cool, just plug this into the calculator and let it go. So let's get out of this by doing second mode to quit out of this. We're going to do 125 plus math 9 to do an integral between 0 and 12 of vars right, enter 3 with respect to x. And we get, come on, 122.026 if I'm rounding. So 122.026. And again, it's not asking for units, but you should be comfortable giving the units. We're talking about how many gallons of heating oil. It even asked it in the question. So this is going to be gallons. All right, last question. At what time is it the least? All right, it's the whenever it asks for this word least, it's asking for the absolute minimum. That's another way of asking it. And show the analysis. Our analysis is going to be a table because it's an absolute minimum. Always going to be used a table for absolutes. So let's go ahead and set up our table. We have a horizontal line here. We'll have a vertical line. Please turn into a straight line. I guess I picked up the pencil. I don't feel like I am, but if you say so, software. Is that enough room? I'm trying to think. I don't think there's going to be that many values on this one. I'm trying to remember the graph. The graph didn't have like a whole bunch of x-intercepts. I'm going to come back here to graph. Yeah, it had just like 2 values, so it should be pretty short. Label our columns. So this is going to be t values. This is going to be start values plus change values to get equal to our end values, and we're looking for the smallest. All right, we always have to have 0 and 12. So 0 and 12 go in the table, and then I need to find these 2 x-intercepts on the graph. So I'm going to do second trace to do a 0, so 2. My left boundary, I'm just going to hit 1. Right boundary, I don't know, 6. And I'm going to guess like 5. And I get 4.790. So 4.790. And the other one, might as well have it on the table too. So second trace to do a 0. It looks like it's basically at 12, right? I know that the window is between 0 and 12. So I'm going to guess that it's between 10 to 12. And I'm going to guess it's like at 11, I guess. I don't know. And it's 11.318. 11.318. All right, so one of these we don't need. Which one is it? So since we're looking for a smallest value, remember the definition of, are we talking about mg? What is our function called again? Oh, it's h minus r. Well, I'm just going to call it f. An f relative minimum is the potential f absolute minimum, and the definition of an f relative minimum is where f prime, which is the graph that we're looking at, so heights on this graph, where heights of the graph go from a negative to a positive. And notice that the first value that I gave you, 4.790, this value is an absolute, not absolute, this is a relative maximum, which means I do not want to do it. It's probably going to be this one, or this one. So in my table, I'm going to go ahead and explain here. I'm going to cross out that value, zoom out and say, nope, not going to do you. Why? Because this is a relative max, which can never be a minimum, and do the rest of them. So our start condition was 125. Yep, I got that right. 125, 125, 125. And then I'm going to add some values. Our integral is going to start at 0. I remember that start condition. Integral from 0 to whatever that value over there is. 0. 11.318. 11.318 and 12. Just punch these into the calculator. So that first one is pretty silly. You don't have to do anything. Oh, I should probably fill out these integrals. I keep reading my letters. Is it h minus r? Yep. So it's going to be capital H of t minus capital R of t, that quantity dt. That was a lot of writing. Is there a way in this? I don't know the iPad very well. Can I copy all of that? If I just hold it down, can I copy? Then I have to hit like paste over here. So I should just hold down paste. Lovely. That's pretty cool. That does save some time. Cool. And punch this in the calculator. So let's do second mode to quit out of this. I'm going to do, oh, well, check this out. I already did 0 to 12. I should write that one down as well. This one is 122.026. And I can just do second enter to do the previous line and change this 12 into 11.318. 11.318. And we get, go calculator, you got this. You have to show the calculator some love. All right, 120.738. And then that one is just 0, 0, so that's just 125. again, we're trying to find the least. Which one is smallest? Well, 120.738 is the smallest. So write out your conclusion. We'll say the volume is the least. Is the least at time t is equal to 11.318. 11.318 with a value of 120.738 gallons. Cool. And do they want us to like round to the nearest gallon or anything weird? Nope, just that. Cool. And that was the last one. Oh, part D. Cool. Zooming out to see all the problems. Number 8, another calculator question. We don't have two equations, we just have one equation, so let's go ahead and enter that equation, get rid of those. So it's going to be 5 square root of t, then hit the right arrow key so I'm not underneath the square root, then cosine of that t divided by 5. It looks like, yep, the divided by 5 is on the inside of the parentheses. We're looking good. All right, let's get out of that. Do we have any window that we know of? Oh yeah, so it says up here between 0 to 31. So I can say window 0, enter 31. And then I'm going to go ahead and zoom 0 that. While that is thinking, let's come back and analyze our problem. The first thing that I'm noticing after the window is that it tells us an initial amount and an initial time. So let's go ahead and label those so we don't forget. This is our start condition. Start with 1000, and we're going to start with time is equal to 0. That's the beginning of our integral. Okay, part A, show that the number of mosquitoes is increasing at time is equal to 6. So whenever you have this keyword increasing or the keyword decreasing or both, it means take the derivative of the thing I was talking about, the number of mosquitoes. So this is really asking for number of mosquitoes prime, and cool thing for us, we have a number of mosquitoes prime because that is the rate of change of the number of mosquitoes. That's literally the same thing. So R of t is what it's asking for. It's asking for R of 6 here. So I come up here, this is asking, what is R of 6? R of 6. And we can just do a trace for that one. That one's easy. Trace 6, enter, done. 4.437. So 4.43, I guess it's 438 if you round up, right? I just want to mention that if you don't want to do it as a trace on the calculator, if you like just you're looking at this, you're like, oh, how do I find that? There is another way of doing that, and that's doing vars right, enter, enter for y1 of 6, and you'll get the same answer, 4.438. Just showing you two paths to get there. And check it out. This number that we got, R of 6, is a positive number. So therefore it is increasing. Do we need to say anything other than that? I'm just going to go ahead and have like a final conclusion, make sure they know that I know that. So I'm going to say that the number of mosquitoes, did I spell that right? Mosquitoes. I never do. I should probably look at how they spell it, huh? That'll be faster. Mosquitoes is increasing. Why? Because that thing that I just found, R of 6 is positive. It's greater than 0. Good enough for me. What about B? At time t equals 6, the number of mosquitoes is increasing. Or is it increasing at an increasing rate or increasing at a decreasing rate? Well, I mean, it's definitely increasing. It already told us that in the last problem, right? So it says, yeah, it is increasing. Now it's asking about the second derivative. Is it increasing at an increasing or decreasing rate? And we need a reason. There's two ways to do this. You can either take the derivative on the screen that we're currently looking at, or do it graphically. I think that graphically is the fastest way to do it. If you just do like a trace 6, enter, you can say, oh, look, the height here is positive, which means that this number was positive, and the slope of this graph, aka the derivative of the derivative that is already being graphed. Again, you're basically graphing the derivative, right? If I take the derivative again, you're talking about the second derivative. And in terms of the slope, height, concavity, all those words, we're talking about slope now. Notice that the slope over here on this graph is negative, which means that our second derivative is negative. That's the fastest way to do it. But there's another more formal way to do it, and I'll show you that way as well. You can take the derivative of y1, so you can do a math 8, the derivative with respect to x of vars right, enter, enter, of y1 at that spot 6, and you should get a negative number, and indeed you do. So however you want to do it, you just have to say that it's negative. You don't have to give the exact value, but I'm going to because I'm cool like that. I'm going to go ahead and say that r prime of 6, oh, I want to be in writing mode, ha ha ha, I haven't done that in a bit, r prime of 6 is equal to negative 1.913, which, as it happens, is a negative value. So we'll say our final conclusion is the number, I don't like writing out the word no mosquitoes, I got it wrong. I'm just going to say the number is increasing at a decreasing rate, at a decreasing rate. And why? Because the thing that we just found, r prime of 6, happened to be less than 0. And you could have done that graphically, or that second way that I just showed. Part C. According to the model, how many mosquitoes will be on the island? Okay, what is the end amount of mosquitoes at time is equal to 31? We have to take into account our start conditions now. Our end amount is at time is equal to 31. So it's always going to be start plus change is equal to the end. And our start, I totally forgot what it was. There's 1,000 for our start. So we're going to have 1,000 plus the change is going to go, oh, the integral is getting a little bit sloppy there. Better. I think that the time starts at time is equal to 0. Does it say? Yeah. It says time is equal to 0. I see it up there. So time is equal to 0 to that 31 that it's asking for of that function. What letter is r, right? Yeah. R of t, I hope, dt. And you just enter that into the calculator and it spits out an answer. So 1,000 plus math 9 from 0 to 31 of vars right, enter, enter, with respect to x. And it spits out, please. Oh my gosh. There it goes. 964. 964.335. 335. I just have one of those feelings like I should really reread the question. According to the model, how many mosquitoes? Got it. Oh, okay. See? Second part of the question. Round your answer to the nearest whole number. So if this number is a 5 or greater, then round it up, but it's less than 5, so round down to 964. So the answer here is going to be 964 mosquitoes with an E. And I probably should box that so people don't mistakenly think, oh, this person might have meant 964.335. No, pay no attention to that. We know we're supposed to round. Oh, wow, we're already on part D. Calculator questions go so fast. To the nearest whole number, okay, that's going to probably come back to bite us. Will we remember to do the nearest whole number? This is going to be the piece that we'll forget. We're looking for maximum, absolute maximum, so we're going to need a table. And just once again, you're like, oh, it's probably a table because there's all this empty space. On the real AP test, you won't have all this empty space. Every single question will have the same amount of space. C and D should have half a page each. Show the analysis that leads to your conclusion. All right, the analysis will be a table. So we need a horizontal line. Thank you, technology, for fixing my lines. That is probably way too big. I don't think there's going to be that many values. Whatever. Let's go ahead and label in here. We have t values. We have start. We're going to add our change. And we should get our end values. And we're looking for the max. We're looking for the biggest one. So you always want the start and end. So 0 and 31 always have to be included. So 0 and 31. I don't think there's going to be that many values. And then we need all relative extremums. So if I come back to my graph, okay, well, there's 2, so maybe I do want to move this down a little bit. There are 2 values. Let's go ahead and find them. And my gosh, those are lots of tick marks. So I'm going to do a second trace to do a calculation of my 0. Yeah, left boundary, there's good. I think 12 is probably too big. Good enough. And I'm going to guess 10, I don't know, somewhere around there. 7.853. So this is going to be 7.853. And then let's go to the second one. I'm going to guess it's around 15-ish. I'm not sure. So second trace, and then do a 2. Left bound, I think 10 is excellent. The right boundary, I'm going to go with 31 because it's all the way on the right. And anything in between, like 25, is fine. Oh, that was kind of close-ish. 23.562. 562. Okay. Well, again, we're after a maximum, so it wouldn't make sense to include that last value because that's a relative minimum, just as a way to remember that. And by the way, I want to fix up these lines with my precision eraser. Get that all the way squared away. That looks better. I'll change this back to stroke so I remember. The definition of we're talking about an R, right? Yeah, so an R relative maximum, the thing that we're after, because you have to be a relative maximum in order to be an absolute maximum, is when you have an R prime. I have to be careful because I want to say an R prime. Well, R is already a prime, so I guess I'm correct in saying that's an R prime going from a positive to a negative. Really what I'm after here is this. This is not very good notation. I'm realizing that, because really what I want here is kind of like, this is really what I want to say. Because at the end, the overall maximum of R, the number of mosquitoes, and then you take the derivative of the integral and get back to just R. Whoa, I did not mean to erase all those. I apologize. That's kind of what I want to say, but whatever. I'm going to leave it like that. We need a height that goes from a positive to a negative. That's the main thing. Look at this graph over here on the left. Do you see a height go from a positive to a negative? Yes, you do with this t coordinate of 7.853, but with this 23.562, it goes from a negative to a positive, which is a relative minimum. So that one can be excluded, and we'll even say that as well. We'll say cross that one off because that one is a relative minimum, which can never be a maximum. Cool. All right, so our starting amount for all of these is 1,000 mosquitoes, 1,000 mosquitoes, 1,000 mosquitoes, and then I'm always going to do plus this integral that goes from 0 to, in this case, 0, and it's going to be capital R of t dt. And I should zoom in here so my handwriting looks nicer when I zoom back out. Plus integral from 0 to, what was our value? 7.853. 7.853 of capital R of t dt, and plus this integral from 0 to 31, right? Yeah, 0 to 31 of capital R of t dt. All right, just got to punch these in the calculator. Again, this first one you don't have to worry about because that's just 0. So the first one is just 1,000, which makes sense because there are 1,000 mosquitoes when I begin, and then I have to do this next one. So quit out of this. We're going to do, basically that last integral. So I'm going to do a second enter. And I actually have 0 to 31 already. So that one was 964.335. And we only need to do this new one, which means this one is going to change to 7.853. And what value you're going to get for that? I'm going to guess probably the maximum, somewhere over 1,000, I would hope. Please. Yeah, there we go. 1,039.357.357. Cool. And I didn't forget nearest whole number. So I'll round that in my final answer when I'm saying it down here. I'll say, and I want to zoom in here, the maximum number of mosquitoes. I'll try to spell mosquitoes again. Is at time is equal to, what was it, 7.853. 7.853 with 1,039 if I'm rounding. Yeah, 1,039. 39 mosquitoes again. Mosquitoes. Cool. That looks good. I don't need a box check conclusion. That's pretty straightforward. That is the answer. Number 9, yet another calculator question. And I'm noticing that we have an equation, so we might as well plug that equation in for our velocity. So our velocity function is sine of that t squared. Cool. And our interval, our window is between 0 and the square root of 5 pi, so the square root of 5 pi. Good. Zoom 0, and we should get that exact graph that is shown to us. Yeah, looking pretty good. Reading. Okay, so it has some start conditions that we want to be wary of. The start position is 5, so 5 is the start position. Good. All right, question letter A. Find the acceleration of the particle. Okay, well, we have velocity, and we want to get to acceleration. If I take the derivative of velocity, I get acceleration. So the way that I'll annotate that is I'm looking for acceleration at time is equal to 3. That is given by taking velocity and taking its derivative at 3. And we know how to do that. We can get out of this graph, and we can say math 8, that's the derivative with respect to x of var is right, enter, or y1 at x is equal to 3. And we get negative 5.467, I suppose. So negative 5.467 with the rounding. And that's all there was for that problem. On to part B. Find the total distance traveled. Okay, every single time I think of total distance traveled, I always think absolute value. Total distance traveled is always the absolute value question. That's the only one that you have to remember for absolute value. And it's between 0 and 3. So I need to set up my formula. And the formula is the absolute value of velocity. And the bounds are going to be between 0 and 3. So I'm going to say this is going to be the integral between 0 to 3 of the absolute value of velocity, dt. And I just typed that into my calculator. So I'm going to do math 9 to do the integral between 0 and 3. And I want to do absolute value first. So that's going to be a math right enter, that ABS, right? Absolute value of v, which is var is right, enter, and with respect to x. And that will also spit out an answer. And I'll zoom in here, getting ready to write this as soon as it's done. This is equal to 1.702. 1.702. And there's no other part for that question. It's going kind of fast. It's nice. Find the position of the particle. All right, so this is kind of like the end position, right? Where is it? So we need to account for our start condition at this point. So this one is going to be start plus change is equal to an end. And that makes sense because we're given velocity and we want position, so I need to be doing some sort of integral. That's going to be our change. Our start position again was 5. So this is going to say 5 plus the integral. The starting time should have been 0, right? Yeah, it says x of 0 is equal to 5. So this is going to say from 0 to the time that's asking for, which is 3 in this case, of our velocity function, dt. And you just plug that into the calculator. 5 plus math 9 between 0 and 3 of var is right, enter, with respect to x. 5.774 if I'm rounding correctly. 5.774. And there's nothing else asked for that question, which means we're on to part D, which has to be a little bit harder, right? This was too easy so far. All right, so on that interval that we originally graphed this, find the t at which the particle is farthest to the right. And there's a bunch of little waves there. This is going to be a little bit tricky. But the way that I am interpreting this is a maximum. Farthest to the right is the same thing as a maximum. So I'm going to underline this. That's the same thing as a max question. If it was farthest to the left, I would interpret that as a minimum question. So the absolute max, you need a table, and that will be the explanation of your answer. So let's go ahead and make our table. Straight line, straight line, straight line. I think down to there should be fine. Don't think we need that much room. It's a calculator question, so you just need to enter it in correctly. We have t values. We always want to have our start and our end. And oh, okay, I remember there's a lot of crossing happening here, so maybe I need this line to be longer. We'll see. Maybe I can squeeze it in here. The square root of 5 pi. I need to find each and every one of those. And then I'm going to have a start plus change, and that's going to be equal to an end. Oh, I didn't mean to do that. Where was I? Thank you for still being, for still working. All right, so if I come back here to the graph, I need to figure out each of those values. And okay, it's going to be a lot of work to find 1, 2, 3, 4, 5. Is that right? 1, 2, 3, 4. Just 4. 1, 2, 3, 4. Yeah, there's 4 times that you cross the x-axis that are not the start and end. You don't have to do all 4 of them, because we're after a maximum. And just as I've said this over and over by now, but you're looking for, our function is an f. What is our function? V. I think they're just calling it v, right? So if I'm looking for a max, that means I'm after a v changing from a positive to a negative. It's kind of like an f prime. Let me give the old definition. The old definition was a little bit too small. The old definition was f prime changing from a positive to a negative, but since f prime is kind of like the same thing as v, that's why I just swapped it out for the v. We're essentially looking for a v height, because this is a graph on the calculator of v, a v height that goes from a positive to a negative, which means it's kind of hard to annotate this screen. Is there a way to take a screenshot? I'm not going to learn how to do that right now. It's probably too inefficient. But it just means we get to avoid more values. So this first value that happens at about 1.7, 1.8 is a good value because it's going from a positive to a negative. So let's go ahead and find that one. So I'm going to do a second trace to do a 0. So 2, left boundary 1, right boundary 2. I'm going to guess 1.7-ish. I get 1.772. 1.772. The very next value, if I go to trace here and go to this next value, this, I think that's how I'll annotate it, right? This value is not a good value, right? Where the cross of the x-axis between these 2 points is not good because it's going from a negative to a positive, which is a relative minimum, and we're after maximums. So I'm going to totally ignore doing that value. I'm not going to even add it to my table like I've been doing previously because it's just too much work. The next value that I want is this value right here. So I'm going to go ahead and do a second trace to do a calculation of the 0. So 2, left boundary, I'm just going to hit left a few times, enter, right a few times, enter, and guess right there, enter. And I get 3.0699, so I guess 3.070. 3.070. And again, if I go to trace again, if I go to the next point, this next point goes from a negative to a positive, which is a relative minimum, so I'm going to ignore that as well. And then by the time we hit the x-axis again, we're at the very end, which we have already accounted for with the square root of 5 pi. Cool, we have our 4 values to check. Our start condition, again, is still 5. So I'm going to say this is going to be 5, 5, 5, 5. And then we're going to add our integral, a little bit squished at the top. Our time starts at 0, right? Yes, from 0 to whatever the thing I'm looking for. So this is going to be from 0 to 0 of v dt. This is going to be the integral from 0 to 1.772 of v dt. This is going to be integral from 0 to 3.070 of v dt. And finally, the integral from 0 to the square root of 5 pi of v dt. All right. I got a lot of entry to do. Well, okay. I mean, the cool thing about the first one is that you don't have to do that integral. It's just 5 because it's 0 to 0, right? So I'm going to come back over here and say the end here is 5. That one was an easy one. And then after that, I need to actually do some math. So I'm going to do that initial condition so I don't have to do it later, plus math 9 from 0 to 1.77. I hit it twice, I thought. 772. Oh, hit 2 to go to. I forgot to do the rest of this with respect to x, and this is as far as right. Enter, enter. Okay, now that won't work. 5.895. So 5.895, and then I'm going to do a second enter to go back and edit that and change it to 3.070. So 3.070. Oh, 070. There we go. And we get 5.788. 5.788. And finally, the whole integral. Have we done that before somewhere? No? Okay, we do have to do it now then. So I'm going to do second enter yet again and change this to a square root of 5 pi. So second square root of 5 pi. And then get rid of all this stuff. So delete, 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 delete. And hit enter. And we get 5.752. 5.752. We're looking for the max, the biggest, and 5.895 is the biggest. So I'm ready to make my final conclusion down here. So I want to say farthest to the right. So zoom in so my handwriting looks better when I zoom back out. The particle, maybe I should use this writing mode. I don't know. The particle is farthest to the right at t value is equal to, what do we say, 1.772. 1.772 at position 5.895. Whoa, what just happened there? That's weird. 5.895. The mysteries of the iPad, we'll never know. I will. Just give me some time. That's as far as we can go. I think that's the whole problem. Yeah, that was part D. All right, problem number 10. You've got Karen riding her bicycle on a straight road. Cool. This is a graph of velocity. It's over 12 minutes. We're in miles per minute. All right, so far so good. Okay, let's move on. Find the acceleration of Karen's bicycle at time is equal to 7.5. All right, interesting question. We're given a graph of velocity, and it's asking for acceleration. We all know that the acceleration is the derivative of velocity, and since we're given a graph of velocity, the derivative on any graph is the slope. So it's really asking, what is the slope at 7.5 on this graph? And again, that's going to happen right around here. So let me go ahead and draw an exact line of what that looks like. So at this spot, 7.5, at that point, what is the slope of that line? And most people will say, oh yeah, well, it's going down one, right one. And you would be correct, kind of. Remember that the units for the y-axis are not scaled the same. They're scaled by 0.1, 0.2, whereas the x-axis is scaled by 1, 2, 3. So different scaling, just be careful. Use the definition of slope here. So we're after acceleration at 7.5, a of 7.5. And that's going to be equal to v prime of 7.5, and that's going to be equal to slope. So I'll make a note here. This is slope at 7.5, and for us that's going to be, I'll give the general speechy definition. I always like giving those as often as possible. It's f of b minus f of a all over b minus a. In this case, we're going to have some y coordinates. So our y coordinates, I'm going to do 0.2, then 0.3. So 0.2 minus 0.3, all of this divided by 8 minus 7. 8 minus 7. I don't know if I'm showing my work there enough. Here, let me go back a previous step so you really understand what's going on here. This is going to be f of 8 minus f of 7. And maybe I shouldn't be using f. Maybe I should be using v. Whatever. I'm going to do f. f of 7 all over 8 minus 7. And that is now going to be equal to this function. this fraction. All right, so I'm going to get a negative 0.1 in the top, and I'm going to get 1 in the bottom. So that's just a negative 0.1. And it does say to indicate your units of measure down here. So make sure we have the right units. Because we're talking about acceleration, it should be unit per time per time. So we have velocity is miles per minute. So it should be miles per minute, or miles per minute squared. I'm just going to go miles per minute squared. That's kind of the classical way of writing it. So I'll say miles per minute squared. Cool. That's our final answer. And then we move on to part B. All right. Using correct units, explain the meaning of that thing. All right. What did I just say in the last problem? I said that you only have to have one absolute value definition memorized, and that is total distance traveled. So that's what that means. It is the total distance traveled between 0 and 12. And then we need to find it. Okay, so there are two pieces. Don't forget that there is a second piece. So I'm going to go ahead and rewrite this thing. I'm going to say that the integral between 0 to 12 of the absolute value of v of t, and then dt is on the outside, right? Yep. So end absolute value dt means, and that's the total distance traveled, means the total distance traveled between 0 and 12 minutes. I guess the total distance traveled in miles. We should have units here, right? In miles. Between 0 and 12. Oop, my 0 is a little bit too small. Between 0 and 12 minutes. Excellent interpretation, Mr. Sindel, if I do say so myself. And then we're moving on to the value. Okay, so to find the value, essentially, we're just finding the area under the curve, but anytime that we have a negative area, absolute value means it's positive. They don't cancel each other out, because normally, like right here, right, these two would cancel each other out because they're the same shape, but they're now both positive. So really, I have another triangle up here if I kind of reflect this triangle up here. Anyway, bunch of areas. Let's go. I have a triangle. Base is 2. Height is 0.2. So I'm thinking 0.4, but it's half of that, so it's going to be 0.2. 0.2. This is also going to be 0.2. It's the same exact shape. All right, I want to divide this one up. Okay, so that mark is getting in the way, so I'm going to move you. I have a triangle right here. Whoa, I wanted that to be a straight line, but I guess I lifted up the pencil again. It's being kind of finicky. There's that straight line. I'm seeing this rectangle here. I'm seeing this triangle here. That leaves that rectangle with this triangle piece over here. All right, so we've divided it up into all the pieces. Our first triangle between 5 and 6, it has a base of 1, a height of 3. 3 times 1 is 3. Oh, I guess I should say 0.3, right? But then half of 0.3 is 0.15. And then this is a rectangle that is 1 by 0.3, which is just 0.3. And then I have that really, really tiny triangle right here, which I won't be able to annotate inside, so I'll put an arrow and say that's 1 by 0.1, which is 0.1, but half of that is 0.05. Be careful with your decimal places here. Next, we have this rectangle, which is going to be, so I'm going to count 4 to the right, so 4 times 0.2 is 0.8, and then it's not half of that, it's just 0.8. It is a rectangle, right? And then finally, we have this triangle between 11 and 12, which has a base of 1, height of 2, height of 0.2, I should say. That's going to be 0.2, but half of that, because it's a triangle, which is going to be 0.1. All right, lots of little mental math games there. I'm going to add them all together now. Will I have enough room? Okay, here. I use technology, so I can just copy and paste this down below. So essentially what I have is I have 0.2 plus 0.2 plus 0.15 plus 0.3 plus 0.05 plus 0.8 plus 0.1. And because of technology and it being so awesome, I can grab that and just move that down here. Right about, yeah, sure, that looks good. And what I can do now is I can say that this integral between 0 and 12 of the absolute value of v of t and absolute value dt is equal to those numbers added up. Is there a fast way to do this? don't know. So the first thing that I see is this point with 15 and 0.05 adds up to the 0.2. And then I have 3 of those 0.2s. Now I have that one that I just made and the first 2, which is 0.6 plus, and I should be maybe annotating that. So I have, that's 0.2, another 0.2, another 0.2, so that's 0.6. Now I'm up to 0.9. Now I'm up to exactly 1, and then 1.8. Cool, so that seems to make sense to me. I hope that I did that right. If I make a mistake, then I'm going to have to redo this video. So this is equal to 1.8. And my calculator I haven't been using, so I need to go ahead and reset it, which is kind of annoying. I haven't used it all this this problem, which is kind of nice. Oh, I guess I could have used it right there. All right, whatever. Find the value. We did find the value. It doesn't say to indicate units, but you should know that we just did an integral there. So that means we got rid of a unit of time. We used to have miles per minute, but we got rid of the per minute, so we just have miles, which makes sense because that's the total number of miles that Karen biked. So you don't need it, but you should be comfortable knowing that that is miles. Moving on to part C. Shortly after leaving home, Karen realizes she left her calculus homework at home, and she returns to get it. At what time does she turn around to go back home? Oh, so this is just like an interpreting a graph question? That's kind of cool. So mathematically, in terms of calculus, speechy definition, what's going on here is it's asking, what is a turnaround point? What does that mean? Well, that's a V sign change. Like you were going one direction and then you're going a different direction. That's negative. Like you were positive, then you're negative. So a change in direction is a V sign change. That's the definition I'm getting at. So I'll say change direction. You should know that that means V sign change. And where does that happen on a graph? So you can see up here with my little laser pointer, it happens right here. We were a positive and then we were a negative down here, and that happened at 2. So I'll come down here, write our final answer. We'll say that she turns around at time is equal to 2 minutes. I'll just say 2. Why? And it's because that was the V sign change. Because V sign change. Is that all one word? Do I need those hyphens? Ooh, that was too big. Okay, I guess I'm rewriting it. Because V, what is going on with my handwriting? V sign change. Good enough. All right. Did I answer all the question? Give a reason for your answer? I did. V sign change. All right, part D. All right, now that I've reset the calculator by reloading the ROM, I'm going to go ahead and enter in this function. So I'm going to have a y equals, and this is going to be pi divided by 15, and this is going to be times sine. And the reason I'm doing, I think you don't really need that time symbol. It should still work. To prove it to myself, I'm just going to type in sine right now, because that sine should theoretically be on the top since I don't have any parentheses. I assume. We'll see. Sine of pi over 12, and then t, again, I don't think you need a parentheses. You don't need to, like, say times or anything. That x is really on the top. That should now be the correct equation, which looks kind of funky, but there it is. And our window is going to be between 0 and 12. Yep. All right. I don't think we'll need the window. I don't even think we need to graph it because aren't we just after the total distance traveled? No, it's just end position, right? Let me read the question. Who lives closer to school? Yeah, so how far away does she live? And by the way, we haven't figured out how far away Karen lives. We've only done the total distance she traveled. So what we have to do, and this is really tricky. Most students think, oh, okay, well, because we had this 0.2, all we need to do is subtract that 0.2 and we'll get the right answer. No, you would be incorrect in thinking that, because what we did was we took this 0.2 that was negative and made it positive essentially up here. What we need to do is subtract it once to get back to 0, and then subtract it again because now it's negative. You have to subtract 2 twice in order to figure out the total distance that Karen lives, and it's on purpose. This is supposed to be a tricky question. I would like to explain that more, but I'm a little bit tired right now. You can kind of see it's 1:28 in the morning. So I'm going to go ahead and say, you need to subtract it twice. Or even better yet, here's another way to think about it. Go ahead and make this a negative 0.2 and then re-add those all together, and you'll see, oh yeah, you do need to subtract 0.4 for some reason. Anyway, she lives 1.4 miles away from home. So for Karen, I'll go ahead and annotate it this way. Is there a value for Karen? I guess it's just V. So I'll annotate it this way. Karen is Karen. Karen is going to be the integral from 0 to 12 of that velocity function that we had, v of t dt. And we know that's going to be 1.4 miles. But for Larry, the only way we can find Larry is by doing the integral from 0 to 12, is it? Yeah, so it's still between 0 and 12. 0 to 12 of that lowercase w of t dt. And that's why we need the calculator. So I'm going to get rid of this. Math 9, between 0 and 12 of our vars, right, enter, enter, with respect to x. And Larry, how far away do you, oh, exactly 1.6. Okay, I thought it was going to be like some weird decimal, but there you go, 1.6 miles. And that's all we needed to do. So we need our conclusion, I guess. We're asking who lives closer. Okay, so Karen lives closer. So we'll say Karen lives closer to school than Larry. Closer to, I was SCHOOL. Okay, for some reason that's looking weird. I think it's just too early in the morning. To school than Larry. I don't need to show any extra work because I showed it all up above, so I think that should be good enough. Cool. I think that's all the problem. Let's zoom out. Number 11. We're 2 questions away from almost finishing the free response question packet. We've got our dy dx is equal to x squared, all that stuff. All right, and we have just a, b, and c. I have a particular solution for part c. That looks fun. This is kind of funny too. It's saying use the axes provided in the pink test booklet, which we don't have, but those were the original instructions from the 2004 test. All right, so the first thing, let's do the slope field. So the way that you do that is you plug in all of your x and y coordinates. So I'm just going to start on the left. I'm going to start at this point over here. So notice that I have an x coordinate of -1. So when I plug in -1 over here, I'm going to get -1 squared, which is just 1, which means I can essentially ignore the fact that that is -1. In fact, all of these, I'm going to ignore the fact that x is -1. And I'm only going to worry about the y coordinate. The y coordinate is 3 for this point right here. So 3 minus 1 is 2. I need a slope of 2. I'm going to attempt my best slope of 2. It looks good. And then now I'm going to have a 2 minus 1. 2 minus 1 is 1. So I want a slope of 1, which looks like that. And then 1 minus 1 is 0. I'll have a slope of 0. Thank you, straight lines. And then I'll have 0 minus 1, which is a slope of -1. So a slope of -1 looks kind of like that. Good enough. I mean, if I want to be super exact, I could shift this over. Is it going to let me? I'm still getting used to the iPad. All right. And the cool thing that I can already see in advance is plugging in 1 versus -1 for the x coordinates does not matter, since I'm going to square that x coordinate either way, which means I have the exact same lines over on the right hand side. So I can just copy that and paste that over here and paste those same lines. And I think, where was I? Ooh, this is kind of difficult to do. Looks good enough to me. Cool. And now I need to figure out what happens when the x coordinate is 0. Well, when the x coordinate is a 0 here, that means that this is 0, and 0 times anything else is 0. So all of these are going to be 0. So slope of 0, make it a nice straight line. Slope of 0. Oop. It thought I wanted to be a curved line because I'm so bad at making straight lines. Whoa! I double tapped it with my palm, I guess. Straight line. Straight line. And it's kind of hard to see, but that is a straight line. All right. Cool. Moving on to B. Yep, we only have 12 points. I'm just reading here, describe all the points where the slopes are positive. Okay, so the way that I think about this problem is dy dx is synonymous with a slope. This is saying the slope is this function. So if I want this slope to be positive, this thing needs to be positive. So let's go ahead and rewrite that. I want the dy dx to be positive. So I want, how do I want to say that? Since these two things are the same, this is dy dx, I want this thing to be positive since they are the same thing, right? This is equal to dy dx, therefore this needs to be positive. So that's what I'm going to say. I'm going to copy down that x squared times y minus, what was it, y minus 2, I think? Oh, no, it's y minus 1. Y minus 1, this thing needs to be greater than 0. And then I'm going to solve. Well, if it's greater than 0, it does, like, having x is not going to affect anything. The reason that x is not going to affect anything is, like, it's always going to be positive. So I'll make the note here that this x squared is always positive, which means it's not going to affect if it's negative or positive. So essentially, I can now come to the line, okay, well, check y minus 1. Is that greater than 0? Or why did I say 1? I said it in words correctly, greater than 0. Oh, well, that only happens if I add 1 both sides. That only happens when y is greater than 1, and that's the answer. Y has to be greater than 1. So I'll write out in words what I want to say. Slopes are positive when y is greater than 1, but you also have to be careful, because what if x was 0? If x is 0, then everything is 0, and the slopes are neither positive nor negative. So you have to say slopes are positive when y is greater than 1, and x can't be 0. And x cannot be 0. Cool. And okay, this is going to be the bigger part. So whenever you see the words particular solution, you are going to do those 3 steps, 4 if you're going to go for that extra point. Separate, integrate, evaluate, and maybe isolate if you have time. So let's go ahead and I'm going to rewrite the problem before I do anything. So the problem was whoa, my handwriting just got like terrible for some reason. Zoom in here. So dy dx is equal to x squared times the quantity of y minus 1. There's the original problem. So first step, and you don't have to write out these steps. I'm doing it to keep my key organized. Step number 1 is to separate. Separate just means I'm going to cross multiply. So when I cross multiply, I'm kind of thinking of this thing as like being divided by 1. I'm going to get this dy times 1 first of all, and that's going to give me a dy. And then cross multiply the other way, and I'm going to get an x squared times y minus 1 times a dx. Still not separated, so I'm going to divide both sides by y minus 1, and I'm going to get dy over y minus 1. Do want that to be a little bit off to the side, so y minus 1, and that's going to be equal to the leftover, which is x squared dx. All right, my separation of variables are done because on the left side I have y's, on the right side I have x's. It doesn't matter which side is on which, but typically I like my y's on my left and my x's on my right. All right, that was step number 1. We are on to step number 2. Step number 2 is to integrate. So slap on some integrals there, and I'm going to do a little bit of reformatting because really I have a y minus 1 to the power of a negative 1 dy. Instead of having fractions, I just don't like fractions, so I got rid of it. And I have to slap on the integral to the right hand side too as well, so x squared dx. And then from here, I need to actually do the antiderivative. So be careful on the left-hand side. Let me fall into the trap that most students will do on purpose. You'll say, oh yeah, I'm going to do y minus 1 is going to go up to the power of 0, and then I divide by 0, and wait a second, I divided by 0, I can't do that, right? There's a special rule whenever you have a power of a negative 1, and that's a natural log. So oh yeah, we have a house, right? If we have a house, this is our house, and then we have a powerhouse. You need to be careful. Do you need to pay your tax person? So just check y, the derivative of y is just 1 with respect to y, and you don't have to pay your tax person. So just be careful. Sometimes you do have to pay a tax person. This is a case where you do not. So the answer here is going to be natural log of absolute value, y minus 1, and absolute value. Okay, left-hand side, complete. Right-hand side, well, x is going to go up to the power of 3, divide down by the 3, and don't forget your plus c. You get a whole free point for just remembering that plus c right there. All right, so integration, complete. And then I'm on to step number 3, which is to evaluate. Evaluate just means plug in that initial condition. So it gave us the initial condition that when the x value is 0, the y value is 3. So x is 0, y is 3. So I'll come down here. We'll say natural log, I said 3, right? Absolute value of 3 minus 1 is equal to 0 cubed over 3 plus c. All right, just as a reminder, we have our 3 practice finals coming up. For me, for my class, always for my class, you need to keep going. I want you to see what C is actually equal to. But on the real AP test in May, then you stop right here, you get your points, and say, thank you very much. I'm not going to get that point taken away for making a stupid calculation error. But for us, for the next 3 tests at least, you've got to practice this. So on the right-hand side, I get a C. On the left-hand side, I get natural log of 2. I dropped the absolute value symbol because 2 is 2. It doesn't matter if it's absolute value or not. Wow, that one extra step was super hard, right, for my class. I'm just saying that you do have to do that for my class, remember. All right, so that was step number 3, and then I have the gigantic step number 4, which I'm going to come back up here for. Again, this is optional because it's usually only worth 1 or 2 points, and it's a lot of work. So if you want to skip this part of the video, you can, I think in the timeline down below, you can skip ahead to the next part. You can go look at the final question, 12, part A. Step number 4, though, is to isolate. And by the way, thank you for sticking around. If you're in here for the video, it really means a lot to me because it's really hard to do this last step, and it's pretty cool that you're taking on that challenge. To isolate means I need to solve for y, and the way that I'm going to do that is I'm going to look as soon as I finish my integration and then solve for y right here. And in fact, I'm going to rewrite this, but instead of the c, I'm going to change that c out for a natural log of 2 and see what happens. So I'm going to rewrite. I have natural log of absolute value y minus 1, and absolute value is equal to x cubed over 3, and that c is now plus a natural log of 2. All right, and just solve for y, and I'm done. Easier said than done, though. So the first thing that I want to do is exponentiation, because right now the first thing that's trapping us is this natural log. The way to undo a natural log is to have e to both sides. So I'm going to say that the left-hand side is now e to the power of natural log of absolute value of y minus 1. Oop, that should be an absolute value symbol. It hasn't gone away yet. And on the right side, I have e to the power of all of that. This x to the power of 3 over 3 plus natural log of 2. All of that was in the exponent of the e. So the nice thing about doing the exponentiation is that the e and the natural log on this left-hand side over here are going to cancel each other out, and I'm just left with an absolute value of y minus 1. It is still annoying that we have the absolute value, but we will get rid of that in a sec. And on the right-hand side, I could rewrite that, but I'm going to rewrite it in a more helpful form. I'm going to write this as e to the power of x to the power of 3 over 3 times e to the power of natural log of 2. All right, so now is the time where I'm going to do 2 things. The first thing I'm going to do is these 2 cancel each other out, leaving me with just a 2, which is in the denominator. And the other thing I'm going to do is I'm going to drop the absolute value symbols. These 2 are going to be gone, and I'm going to add a plus or minus on the right-hand side. Here we go. So when I drop those absolute value symbols, y minus 1 is on the left-hand side. On the right-hand side, I do have the plus or minus. I'm going to write the 2 out in front. So again, this 2, which came from the e and natural log being canceled out, that 2 is going to come down in front, and I'm going to write that first. So 2 e to the x cubed over 3. And then finally, I just have to add the 1, and I get y is equal to 1 plus or minus 2e to the power of x to the power of 3 all over 3. All right, and you have to choose, is it plus or is it minus? And the easiest way to do that is to just check. So let me go ahead and say, this is my step where I'm going to check to see if it's plus or minus. And the way that you do that, just plug in, again, x is equal to 0, y is equal to 3 to make sure you're on the right track. So on the right-hand side, y has to be equal to 3. I'll put parentheses, let myself sub that in. 1 plus or minus 2e to the power of 0 cubed over 3. Doing some quick mental math, 0 cubed is 0. 0 divided by 3 is 0. So I'll get e to the power of 0. And I'll write this out now. I have 1 plus or minus 2e to the power of 0 is equal to 3. 3 is equal to 1 plus or minus, okay, e to the power of 0 is 1. 1 times 2 is 2. So which one does it need to be, plus or minus? It has to be the plus sign, right? So that means my final answer is made for me. I'm going to rewrite this line, but I'm going to keep the plus and not have the minus. So my final answer, y is equal to 1 plus 2e to the power of x to the power of 3 all over 3. And you better believe I'm going to box that because that's a lot of work, and I want the AP grader to give me that credit. And I'm realizing that box went a little bit weird, so if I drag that corner, that looks pretty. Yeah, zoom out. All right, guys, we're finally there. We're on our last free response question. We're almost done with our first packet. Let's do this. We have a 0.3 comma 1/4, which I see repeated twice here and here. We have a slope. Okay, slope is that. We want the second derivative, which, oh boy, it's not that hard, but it does require a bit of math. So how do we do that? The first thing that we need to know is that if we're looking for the second derivative, we're basically taking the derivative with respect to x, again, of our already dy dx. Why do I write it like this? I just want to remind people that when we're taking the derivative, we're still taking it with respect to x. So take the derivative of that, you're done, but with respect to x. So what does that look like? Well, the first thing I notice is I have a variable here and a variable here, and guess what? They're being multiplied by each other, which means product rule. So 1d2. So 1d2 is going to be y squared is 1, and then d2 is going to be just negative 2. So that's 1d2, and then plus 2d1. So 2 is going to be 6 minus 2x, and d1 is going to be 2y prime. Remember, the y doesn't go away. You still have a y prime out of that. And that is the second derivative. We can make it look a little bit nicer, but I'm not sure how much. I'm probably going to leave it like that for now. Yeah, there might be a better form for that. But let's go ahead and evaluate it. So we found it, now we need to evaluate. Remember to read your instructions. We found it, good. Now we need to evaluate it. So I'm noticing that when we evaluate it, we need a value of y, which we have. We need a value of x, which we have, y, which we have, but we don't have y prime. So let's first find what y prime is. And the way that I'm going to write that is I'm trying to find what is dy dx, aka y prime, when I'm evaluating at 3 comma 1/4. So at 3 comma 1/4. And I do evaluation bar to let myself know that I'm plugging things in. So I'm essentially going to be rewriting all of this, but in the place of y and x, I'm plugging in a 1/4 and a 3. So I have a 1/4 quantity squared, which is our y squared, and that's going to be times 6 minus 2. Okay, here comes my x. My x is 3. and I need to simplify this. So this is going to be 1 over 16 times, okay, well, wait, 6 minus 6 is 0 times 0. That's equal to 0? Oh, lucky us. All right, cool. That's nice. And then I just basically need to do the second derivative, which I'm going to annotate as d squared y over dx squared. You could have just put y double prime. It's just, no, why am I making this so hard on us? Whatever. And again, I'm plugging in 3 comma 1/4. So essentially what I'm doing is I'm rewriting all of this, but in the place of all of these variables, I know what each of those are now. I'm ready to go. So y is going to be 1/4. So I have 1/4, again, quantity squared times -2 plus 6. This quantity of 6 minus 2 times x is 3. And that's going to be times 2 times y, which is 1/4 times y prime. Oh, and this is the 0. Yes, because that was the one that we got from the previous step. And yeah, okay, so I'm already seeing it now. 0 times all of this times all of this times all of this stuff. This whole thing is 0. So I'm just left with, I'll just write it underneath. This is equal to -2 on the top, because again, I'm rewriting this -2. And then this is going to be the bottom, which is going to be 16, which is equal to -1/8. And there's a lot of work there, so I'd like the AP grader to see my work, but also see the answer very clearly. -1/8. And that wasn't that bad. All right, and we are looking for solving that differential equation. Again, it doesn't have the words particular solution, but it's basically doing the same thing. So it's going to have those same set of rules. We're going to first separate. So again, you don't have to write out the rules like I am. You don't have to say step 1, separate. I'm doing it to keep my answer key nice and organized. So separate. And I'm going to kind of think of this thing as being divided by 1, so I can cross multiply. When I cross multiply the dy times 1, I get just dy. Whoa, I want to be in blue though. So I get dy is equal to, all right, cross multiply the other direction, and I get all that stuff with a dx. So I'm going to get y squared times 6 minus, is that 2x, right? I feel like I've seen it enough times at this point, with a dx. All right, we have not separated yet. We need to pull that y squared to the left-hand side. I'm going to say that this is going to be dy over y squared is equal to the quantity of 6 minus 2x dx. Cool. Now I have separated. Step number 2 is to integrate. And I just slap on an integral symbol, but I'm going to go ahead and rewrite that left-hand side because I don't like fractions. Whoa, that integral symbol is not very good. That one is a little bit better. So this is going to be y to the -2 dy, just rewriting our left-hand side without a fraction. And on the right-hand side, I'm just going to rewrite it with an integral symbol. This is going to be the quantity of 6 minus 2x and quantity multiplied by dx. Okay, do the antiderivative. So y is going to go up to the power of -1. Divide down by -1 is the same thing as multiplying by -1, so I'm just going to put a negative out front and call it good. And on the right-hand side, oh, check it out. There's a tax person. Oh, is there a tax person? Okay, there's not a tax person. I thought there was, because I was seeing like the parentheses here. Like, oh, look at this. This is to the power of like 2 or something. No, it's not. You just take the antiderivative of each piece individually. There is no house here. So this is going to turn into 6x minus 2x squared, and then divide down by that 2. And don't forget your plus c. Cool. I mean, I could simplify that a little bit more if I just kind of cross-cancel those 2's, but I'm going to leave it for now. Actually, you know what? No, I'm not going to leave it, because this can be simplified as well, and that can be simplified. There's a few things that I want to change. So the left-hand side is really -1 over y, and the right-hand side is really 6x minus x squared plus c. Now it's nice and simplified. It just looks pretty. And I know that eventually I'm going to use it for my step 4, which is optional, but I'd like to see how many people could do. Anyway, that was step 2. We're moving on to step number 3, which is to evaluate. What are our initial conditions? Our initial conditions, there we have them. So the x is going to be 3 and the y is going to be 1/4. Can I remember that? 3 and 1/4. So I'm going to have a negative 1/1/4. That's the number that was just being plugged in, is equal to 6 times 3 minus 3 quantity squared plus c. And again, I'll make this point again. If you are on the real AP test in May, whatever that date is for your current year, you stop here. Don't make any mistake, because if you make a mistake, they will take that point away. But for my finals, my 3 finals I'm going to have you do, my practice AP test, you need to get all the way down to an answer for C. So I'm going to do that with you. The first thing on the left-hand side, it's a little bit tricky. I have a fraction within a fraction, so I'm going to keep it, change it, flip it. Really what I have is a negative 1/1 in the numerator. So when I keep it, I'm left with a negative 1/1, change it, and then I flip it. That's when I keep it, change it, flip it. And then on the right-hand side, I have 6 times 3, which is 18, minus 3 squared, which is 9, plus c. Simplifying that a little bit more, I get negative 4 is equal to 9 plus c. Subtract 9 from both sides, I get negative 13 is equal to c. So far, so good. And this is the point where most of you will end the video. You are done. But for those few exceptional students that want to go above and beyond and get that maybe 1 or 2 extra points for doing it in a lot of work, then you're going to follow the rest of the video. And I think I might have some few parting words at the very end of this if you want to stick around for that. That might be time-stamped below. Anyway, step number 4, to isolate. Isolate. Then again, I'll tell you, if you're still watching the video, I really appreciate you doing this to go above and beyond. Not everyone does it, and I would say like 20 to 30% of students every year try to do step 4, so thank you for being among that elite. Again, I'm kind of going to rewrite this integration step just like I did in the past problem, but in the place of c, I'm going to change that out for a negative 13. So just rewriting here, we have a negative 1/y is equal to 6x minus x squared, and then that plus the c is really minus 13 now. Minus 13. All right, I just have to solve and I'm done. The first thing that I see is I have a y trapped in the denominator. To untrap that, I'm going to take the reciprocal of the left-hand side, but if I do that, I need to also do the reciprocal of the right-hand side. So take the reciprocal of both sides. As long as you don't divide by 0, that is okay to do. So now I have negative y. I mean, really, this should be y over negative 1, which is the same thing as negative y, which is why I wrote that. And is that's going to be equal to 1 over 6, and okay, I typically write this in standard form where x squared is the biggest one, so I'm going to have negative x squared and then plus 6x minus 13. That looks a lot better. And finally, I'm just going to multiply both sides by a negative, and I get y is equal to the negative version of that. In fact, I'm going to go ahead and be even cooler. I could just write a negative out here in front and call it a day, but I'm going to go ahead and distribute that negative into the bottom, because whenever you multiply by a negative, you can multiply it by the numerator or the denominator, but not both. So I'm going to go like this. Be super cool here, and I'm going to say it's going to be equal to 1 over x squared minus 6x plus 13, which I feel like I could factor that, but no, 13 is prime, and there's nothing that goes into that. And that's all we can do. We can check our answer. The isolate step here was actually relatively straightforward. If I plug in 3 for x, I should get out a 1/4. I want to check it to make sure that that worked. I'm a little bit worried that it didn't. I'll just stay with blue. So this is my check phase, which you don't have to do in this case, but I want to be doubly sure. If we have the option to check our work in AP Calculus, let's do it. We have the time. As I say this, and it's like 2:17 in the morning. It's going to be theoretically I should get 1/4 for y. That's going to be equal to 1 over, okay, in the place of x, change that into a 3. Well, that line was not very straight. Whoa, come back here. 1 over 3 squared minus 6 times 3 plus 13. Does that work out? 1/4 is equal to, that's going to be 1 over 9 minus 18 plus 13. Well, 9 minus 18 is -9. -9 plus 13 is 4, and that's 1/4. Okay, yes, I'll just let myself know that I got it. 1/4 is equal to 1/4, or maybe I just write 1/4 is equal to 1/4. Close to 1/4. It did indeed work. And because I did a check in my work, I do want to make it clear to the AP grader where is my final answer. It's right there. There's our answer. Zooming out so you get to see everything. So final words for everyone. Thank you for doing the free response packet correctly, where you did the problem on your own and only used the video guide for hints and suggestions. You didn't just mindlessly copy this down. And I'm really hoping that no one is in the same boat as me, where you're doing this at 2:18 in the morning or really early in the morning. Number one, because that doesn't sound healthy. And number two, you've still got another packet to do, guys. So please don't be doing this last minute. Try to do it over the course of time. But hey, if you did it early in the morning, you're right there with me. I do procrastinate, even though I'm doing this way before this is actually due 3, 4, 5 days. To me, that's doing it way in advance. Anyway, thank you so much for watching, and I'll see you guys later.